I want to thank Hans for organizing this and inviting me out here. This has been wonderful. I also want to have a shout out to the folks in the back that have been organizing this and making this, taking care of the details, including how to work this projection system. So thank you to the folks back there as well. So I've been asked to give a review talk sort of in the middle of a conference, so it's going to be a little bit odd because I have to, it's hard to give a review without talking about some of the things that have already been mentioned, but hopefully the review, the topics will be sufficiently important that the review will not be amiss, and hopefully I'll have a slightly different take on various topics. And so, so I've been asked to talk about the routes of Oort cloud comets into the inner solar system. And why don't we start by going back to Oort. Oops, I need to get the right, there we are. Here's a plot from his 1951 paper. I don't think it's been shown before here, where he's plotting against 1 over energy and 1 over semi-major axis units, number of comets, and notes this spike here. And in this paper, he talks about various sources for the origin of these comets, including a possible belt of comets that was proposed by Kuiper at about this time. And he talked about stellar perturbations trapping these comets at the appropriate semi-major axis. And the sense I got from the paper is that Oort was pretty much had the "what you see is what you get" attitude about this. That is that these are the comets in the cloud. And it wasn't until a bit later that, why am I, do I have the right one to advance? Yeah, there we are. That Hills pointed out that, well, this is, emphasized that really this is just a selection effect, that what we're seeing are the ones that have remarkably the furthest out are the ones that can see the stellar encounters that will bring them into the solar system, and that there could be possibly a hidden cloud that would only be observed if for a particular close stellar encounter, at which point the entire inner part of the Oort cloud would be exposed would be seen by as comets coming into the Earth. And this could be rather dramatic. If you have if you look at the number of comets coming through, get this thing to start playing. Maybe it won't play. One more try here. Oh well. The movie doesn't work, but the emphasis as a stellar passage comes through, this inner region becomes blacked out with all the comets coming through. And one of the Hills' objectives was to explain how the dinosaurs got wiped out, which was a fun topic at the time. Everybody wanted to know how to kill the dinosaurs. And this was a proposed mechanism to get a lot of bodies coming through in the inner solar system with a high probability of Earth impacts. But there was also, as Morby first pointed out yesterday at about this time, that the galactic tides are a more important part of the evolution of the Oort cloud comets, but they are more regular. And again, as Morby pointed out, these can't be the only thing, because these will not trap comets. If you start down here, sorry, just to get right, this is a proxy for the angular momentum as a function of the galactic argument of perihelion. So if something starts out with high eccentricity, it will be brought up to more circular, but then it'll be brought right back down again. So you're not going to trap comets that way. They're going to eventually return. So you still need the stellar perturbations if you're going to get comets into the trapped into the Oort cloud. I want to make an aside. Speaking of this von Zeipel circulation, you can do the same thing for comets that are approaching the orbit of Jupiter. So here I have a similar diagram, but here the vertical axis is the perihelion in units of Jupiter's radius, and here's the argument of perihelion with respect to the ecliptic. And this this phase-space diagram is constructed in a situation where you have Jupiter as a ring of mass at Jupiter's radius, and so you're integrating the secular equations of motions, and these are the level surfaces. And in such a situation, if you start out, say, with a perihelion near Jupiter, the secular evolution will bring you down into this perihelion that could be Earth crossing, with the consequence that the argument of perihelion is close to pi over 2. And so if you do a simulation where you're throwing parabolic orbits essentially at Jupiter and randomize argument of perihelion and longitude of descending node, and you look at the orbital distribution of the comets that actually get trapped into orbits that are Earth crossing and have periods less than 200 years, then you have orbital distributions that look like this in semi-major axis and inclination and argument of perihelion. And so the obvious thing that was noted is that the inclination distribution is nowhere near the known distribution of Jupiter family comets. But the other thing that wasn't, it's in the paper, but I don't think it's been emphasized in the meantime, was that the argument of perihelion was also inconsistent with the Jupiter family comets. That it peaked at pi over 2 and 3 pi over 2, whereas the Jupiter family comets had arguments of perihelion that peaked at 0 and pi. And just as a personal note, when we first got these results, recall this is back at the time when no Kuiper belt had been observed, and it was this distribution that pretty much convinced me that this result was not just a bug in my code, that this was actually something real, just a personal aspect about that. I think this is kind of a convincing argument that the long period comets cannot be the source of the Jupiter family comets. So you can put all these effects together into a plot of time scales. So this is time scale of an effect on a logarithmic scale as a function of semi-major axis or distance from the sun, and you have period of an object. You have the tidal torquing time from the galactic tide. Note that the stellar perturbation timescale, torquing timescale, also has this same slope, although it's slightly weaker. And then also on this plot is the tidal return time for the tidal circulation, as well as the semi-major axis of energy diffusion timescales for interacting with the giant planets, depending on your perihelion here at 15 AU, or a little weaker at 20 to 35 AU. And so, in this plot, the argument of Oort stands out that if you match the time scale of the tides, that is the time scale in which the tidal forces can cause significant evolution of the perihelion in one orbital time, pretty much defines the edge of the Oort cloud the inner edge of the Oort cloud, and it's right. Furthermore, that time scale is longer than the orbital diffusion time scale, which reinforces the argument that you have to torque a comet all the way across the Jupiter and Saturn in order for it to be observed at the Earth. So a typical orbit looks like this. Here is the evolution in log perihelion and log inverse energy, essentially. And in this simulation, more be noted, we limited computer power, so we started our comets with significant semi-major axis. We had a diffusion approximation interior to this, and we see that you first have evolution in semi-major axis at roughly constant perihelion until you get out to about 10 to the 4 AU, and at which point the tidal torques kick in, and now you have evolution out here at roughly constant semi-major axis. I should point out, right, this work has been improved on by is Luke still here? Luke and collaborators somewhat later. Particularly, they did a better job of evolving the comets closer in. Right, so that's the situation as it stood. We only have the outskirts of the Oort cloud visible. There could be this larger inner Oort cloud, but we don't know much about it or don't have much constraints on it. But this picture had a problem in that the inferred flux of the long period comets, if they only come from the outer port of the Oort cloud, where formation models say that the trapping fraction is actually quite low, that implies you had to have a significant mass of solids in the protoplanetary disk to explain the inferred long period comet flux. And that was somewhat inconsistent with the formation models. So pushing on from there, we have work that Nate and I did in 2009, where we noticed the following, that there is a difference between the orbital elements that you see, semi-major axis, for example, and the orbital elements which the long period comets started out with in the comet. So Marc Bouchard showed similar plots like this. I guess this is classified in Marc's nomenclature. This is a Quinn cave jumper. I feel I need to do some gymnastics here, but I'm getting older, so it should be dangerous. And again, to go through it, right, a comet with low semi-major axis, but interacting Q in the Uranus-Neptune region, experiences some kicks in some evolution in the semi-major axis, and occasionally it will jump to a semi-major axis, where in one orbital period, to be clear, each little diamond is a successive perihelion passage. So after this jump at one perihelion passage, the very next perihelion passage, it ends up with a Q in the visible region. That isn't the only pathway that we noticed. Here's another example over on the right-hand side. Here's evolution with time of the semi-major axis. Similar situation as before. You get some evolution, but at some point you get from Uranus and Neptune, but at some point you get a kick from one of the planets that you notice that the Q is being brought inward. So it's in the part of the secular curve where omega sub g is positive. This jump here turns jumps across into a negative omega sub g. So now the tidal torque brings it out of the solar system along with the jump in the semi-major axis. So this might be a Quinn straggler. Might be the terminology would use for that. Since it sort of switches direction somewhat suddenly. And then there's a third, even less common pathway. And this is a little more straightforward. This is only, say, if you have a comet in the outer part of the inner Oort cloud, then a single stellar perturbation can push it into the Oort cloud proper. And when it gets pushed into the Oort cloud proper, then you see the tidal circulation happening that brings the perihelion into an observable long-period comet. So the point of all this is that the orbital distribution of comets that you see is not the same as the distribution that those same comets started out with in the Oort cloud. So here's a distribution in semi-major axis, cumulative distribution. The observed distribution, that is, as they come into the visible region, is given by the diamonds, mostly in the proper Oort cloud. But the original distribution, before they started interacting with the outer planets, is given by the diamonds here, significantly different. In particular, the comets that you see actually contain quite a few comets and actually half the comets are coming from what we classically call the inner Oort cloud. So you have, right, so there's sort of two implications. The source region is now much larger than what we originally imagined. And so you can have a lower overall Oort cloud population to explain the observed long-period comets, or the long-period comet flux. And then the other interesting implication is that we are observing comets from the inner Oort cloud. So the long-period comet flux really does give us constraints on how much mass is in the inner Oort cloud. And therefore, all right, and so that second point, right, has a couple implications. First, for formation scenarios. So you can imagine, so this is a formation semi-major axis distribution, cumulative distribution in two different formation scenarios. One, the sun's environment was roughly constant over its lifetime. That's the classic. Or it started in a more dense birth cluster, in which case you have a higher number of comets in the inner Oort cloud. So, and those comets, some of which you'll end up as visible LPC, long period comets. And so in this cluster scenario, you also have a larger trapping fraction. So a larger number of these comets can be trapped in the inner Oort cloud. And so as the planetesimal trapping efficiency goes up, then the required mass of solids in the protoplanetary nebula goes down to more reasonable numbers, say, given with a given long period comet flux. And so the second implication is the intensity of the comet showers. So as Morby pointed out yesterday, the key driver to the strength of the comet shower is the indirect force on the sun. And so for a given stellar passage, pretty much independent of stellar mass of the perturber and the impact velocity and impact parameter, it's the delta V of the sun gives you the number of long period comets that get perturbed into the inner solar system by that perturber. And this number is measured as the comets above the background flux over that, usually around tens of millions of years of the comet shower. is how we measure this number. And so, you know, for a given flux, you can get the expected number of impacts. This is based on impact probabilities given by Weissman, 2007. It's roughly a few parts in a billion chance of a comet coming through the inner solar system hitting the Earth. And you see that the comet flux in these showers, say for a given impact, is really not that great, particularly if you're thinking about killing the dinosaurs. So the number of extinction events that we would expect is actually quite low, right? It's over only a few over the entire age of the solar system. Again, based on the fact that we have the lower constraint of the total Oort cloud, inner and outer, and the possibility of a higher trapping efficiency. Well, more the first. And then finally I want to point out, it was mentioned yesterday, can we change the magnitude of the galactic tide? And the answer is, well, we could. And that's because just like the planets, the sun doesn't necessarily stay where it was born as far as galactocentric distance. And so these are simulations, Rock-Roschker, 2009. We're looking at the formation of a Milky Way galaxy, and it turns out that you can have resonant interactions of stars with spiral arms, basically co-rotation interactions, in which case you can get significant migration in galactocentric radius over gigayear timescales. And this was an effect that was first pointed out by Selwyn and Binney quite a while ago, but we saw this in we were initially surprised to see this in our simulations in around 2009. So you can look at these galaxy scale simulations and you can pick out solar analogs to see, that is, stars with roughly the metallicity of the sun at 8 kiloparsecs, and look at their orbital histories. If you do that, you can get orbits which you kind of expect. You know, the orbit of the sun maybe stays the same over gigayear timescales. But there are also situations that something that ended up at 8 kiloparsecs actually started out closer to 3 kiloparsecs and migrated outward. And you can have the situation where you can also have inward migration. So you can have a sun that starts out at, say, 6 kiloparsecs, migrates into 3 for a few gigayears, and then migrates out. So the changing of the amplitude of the galactic tide is a real possibility. And so,
what probability?
Good question. You know, the real question, you know, for our sun, the question is, what is the probability that our sun was a migrator? And there are several, well, the key indication is the sun's relatively high metallicity. So that is an indication that the sun was actually born significantly interior to its current location. I am looking at these simulations to see if there's other indications of that, say, you could measure now for sun-like stars to give other indications or verifications that there's been migration, such as vertical amplitude oscillation and things like that. But metallicity is the key one at the moment. And, you know, I mean, the other interesting, that high metallicity stars seem to be migrators. Right, and so if you do have a migrator, you can, if you look at the, right, we went into the simulations and measured the tide or the vertical gradient of the acceleration field over the history of a typical sun-like star, and you can have quite a variation from what it is at 8 kiloparsecs, considerably higher if it had migrated from say 3 kiloparsecs or so. It's and the other interesting thing about that obviously has interesting effects on the Oort cloud. One particularly interesting effect that we talked about was the possibility. So what we have here is, diamonds are minimum, pluses are median, squares are maximum of the semi-major axis distribution as a function of the minimum galactic centric distance of a sun-like star's orbit. And so for sun-like stars that penetrated within 3 kiloparsecs of the sun can have these minimum Oort cloud objects that are similar to Sedna. And so this could be a possible explanation of sednoids. The one issue is this does not give a preferred direction of perihelion, or argument of perihelion, or longitude of perihelion, I guess it's what is claimed. Of course, that could be, there's arguments about whether that is real, but in this case, we would expect a uniform distribution in the longitude of perihelion, which is not quite what we see at the moment. Nevertheless, intriguing, and we'll see whether the argument of perihelion distribution, or longitude of perihelion distribution, is indeed non-uniform. Lastly, I want to share Megan's enthusiasm for LSST. I think a key observation that's going to be happening real soon is to explore the comets coming in to perihelia beyond Saturn. And taking this plot, probably maybe given time, let's show this plot from Volricki, Nosvorny and Dones, 2019. If we can probe further out in the solar system, then we are going to probe lower semi-major axis. It's kind of interesting paradox there. So in this plot, if we only observe comets that come within 5 AU, this is the semi-major axis distribution that we're probing. As we go further out in the green, blue, and red, we probe further and further in the semi-major axis distribution. So we'll be finally getting real constraints on the inner Oort cloud, which I find to be really exciting. There is a caveat, though, and that is, if you look, right, we already have observations of, well, here they are, a dozen or so, a few more, of comets with perihelia between, between 8 and 12. And if you plot their, and here's their semi-major axis distribution, if you plot their argument of perihelion with respect to the galactic plane, they're all positive, which means that the tide is bringing them into the inner solar system. And so if you try to plot that observed distribution with just a static Oort cloud model, what we predict is this dotted line. And so, and the way we can match the observed is this dashed line is if we fade the comets after 5 perihelion passages. And so this bias, or this distribution that's skewed towards positive argument of perihelion, is indicating that there's significant fading of the comets, even beyond Saturn. So even looking beyond Saturn, we have to take into selection effects if we're going to interpret the distribution we see, say, from LSST to infer the structure of the Oort cloud. So my time is up, I think. I think a main point of this is that even now, just as Jack Hills pointed out in 1981, the distribution of long period comets that we see is strongly influenced by selection biases, which we still have to take into account. Even as we get better and better observations, which I am looking forward to, but that those observations will call for more careful modeling. So I won't be out of a job either. So thanks again for listening.
All right, why don't we start with Hal?
Well, I have a couple questions.
Reminder, name and institution.
Yes, I'm
Just
Hal
for those
Wilson
online.
from Southwest Research Institute in Boulder, Colorado. Can you go back to your last point? So this is when you say you have to fade after 5 perihelion passages.
Mm-hmm.
Right. What were the values of the perihelion before this happened? Were you getting? Can you show you have fading when the perihelion is large?
So, right. I mean, so these are
Be very articulate.
no. So again, so these right. Actually, yeah. So Nate did sort of reverse the orbits here, and generally these are coming from larger perihelia, right?
Which I expect, because that's
where they sit, right? So they are being drawn. So, right, this isn't telling you where the fading is happening, is it? Right?
That's my question.
Yeah. So.
Sounds like an observational.
Okay.
Yeah.
You start from the new comets and you evolve the new comets and you see how many orbits they can evolve.
Well, I played the same game, but I never looked at the issue of when, at what perihelion distance you start to see the fading.
Right. Well, I think sort of being able to detect comets even further out than, out into the Uranus-Neptune region is probably the only way we're going to start answering that question.
That's probably right. So maybe we'll have the answer in a couple of years. I have another question, right?
Let's maybe first go, Bryce, I think you had a question? And then we can go back just to make sure we...
So, yes, I'm also greatly looking forward to the Rubin Observatory, especially its detection comet capabilities. And so what I was wondering, is such a question that I have, is that there's a great deal in difference in the properties between dynamically new and returning comets. Say, once a comet sees the gravity of the sun, its orbit changes quite drastically by an inverse semi-major axis of 10 to the -3 randomly.
Sure, yeah.
So then in that case, you could have, let's say, an object with sufficiently large inverse semi-major axis become somewhat confused with a inner Oort cloud object that is coming into the solar system for the first time, where you'd have a returning comet with the sort of the same inverse semi-major axis that is not a dynamically new comet. So my question is, how do we distinguish dynamically new inner Oort cloud objects from returning comets in this new era of Rubin Observatory?
All right. I mean, I think the thing, right, the kicks from Jupiter, and remember, it's not just direct encounters with Jupiter, right? They're large, right? 10 to the -3.
Mm-hmm.
And so until you start seeing objects with semi-major axes of, say, 1,000, these returning ones are going to be extremely rare, right? Because once it sees Jupiter, it's gone. Or,
But it's random, right? So there are
yeah, there will be a few, but I was going to make the point, it's going to be relatively rare
So I
for a
think
while.
we've got to get ready to set up, but I think it's going to take a minute or two. So how we can come back to your question while they're setting up for the next speaker because they're virtual. So how you got us?
Okay, thank you. Can you go back to your slide that shows the minimum, maximum, and median?
Yeah.
Now, so I'm struck by this, that it seems to me the outer edge of the Oort cloud in this calculation doesn't seem to be particularly affected. Maybe it's just the way you plotted it.
Yeah, well, we're sort of hiding some stuff here, but it is decreasing quite a bit, and it's a logarithmic plot, right?
Yeah.
What is the maximum? Maximum is around the Comet. Right? But this was actually my question. So the difference, you say that if the sun moved in the galaxy, this could be an alternative to the cluster scenario to form a segment.
Yes.
But the difference is that the cluster can be solved rapidly. So you can get Sedna early and then get the normal Oort cloud.
Yeah.
It takes billions of years for the sun to migrate.
Yes.
So if the sun starts at 3, basically you would have a very concentrated Oort cloud and a very anemic outer Oort cloud.
That was going to be my
Right.
question.
I'm not sure you would be able to reproduce the current flux of long period comets that way.
I mean,
All right. So I'm going to say that we should leave that comment
Yeah.
for the coffee break.
Let's talk about it. Yeah.
I know I'm brutal about time.
No, that's good. That's good.
But because we have 2 online speakers who I believe it is very early or very late for, we should make sure we get to them as close to on time. So we have Michele Bannister talking about, from all the way from New Zealand, I believe, the potential for quasi-stellar interstellar objects. So Michele, take it away, and I'll bother you if we get way over time. So take it.
Kia ora. Sound check, is that okay?
You know,
You can talk to her.
does everyone hear Michele?
Yeah.
Is that loud enough?
Yeah, not too much.
Lovely, thank you. Yeah, thank you very much to the organisers for allowing us to do this pair of talks remotely. In my case, because yes, you're not allowed to get on a plane at a certain point when pregnant. So I'm very glad to be able to see you folks from a distance. And yes, it is evening for us. So this is going to be a pair of talks where I'm going to kind of set the scene a bit for what we're trying to work with in interstellar objects. And John's talk is going to go into a fair bit more of the methodological detail of what we've been trying to do here as well. So this is a team effort with a bunch of very astute postgraduate students as well. And we've talked a lot in this so far about comets and the Oort cloud as being an environment in a galaxy, but this is something I really want to focus on here. And I also want to, because now we've got the review talk on ISOs in the afternoon, to just remind us all what I mean when I'm talking about an interstellar object for this purpose. So in this sense, I'm talking about a planetesimal that's unbound from its origin system. So something that has started very much in its planetesimal disk and orbited and undergone an unbinding event that has led to it orbiting in the galactic potential. And so, we have a subsample of this population that comes through the solar system. 1I and 2I are the known examples so far, Oumuamua and 2I Borisov. And this population, though, because it's coming off all of the disks that have been produced in the Milky Way, these are an incredibly numerous population, not by mass, but by number. They are probably the largest in the Milky Way. And so what we've really been working on the last while in our group is to see what we can do to understand the next interstellar objects. And that discoverable population that we'll be sampling within the observable volume of the solar system is really going to depend on the galactic population. So if we're going to have this population, which is incredibly valuable in terms of this is a population that has potentially outlived its stars. right? These are samples of the size distribution of the streaming instability, if that's the dominant mechanism, or of the collisional erosion processes that took place at each of their systems that have then been cumulatively donated to the galaxy over all of the stellar history we have, over all of the planetary history we have. So they're trace particles for all of this. And so we've been trying to put together a model that links together these aspects of planetary, stellar, dynamical, and observational effects, so that we can actually get some predictions in the era of LSST. So in the grand tradition of being inspired by Hal Morby et al. For what you should call these kinds of things, we talked about it in terms of the places that we have been while working on this model. And so this is something where we're looking at, once we release them, what distributions do we have? Where are they traveling? What velocity structures do you get in the galactic potential? And then how observable is that? And I'm only going to touch a bit on the observability today, but Rosemary has a poster that you should definitely go check out for that part of things. So to start with the unbinding, this is something where, as Morby was mentioning right to start us all off, the dynamical instabilities are particularly key. So this is something we've examined here in a numerical sense. So we made about 2,500 simulations in Rebound, each with about 10,000 particles, and populated these in a reasonably close disk inside of 30 or so AU, and ran it for each one for 10 megayears with a sampling of planetary architectures. So just trying to explore the parameter space that you would get for this. And this is work led by Leah Albrow in her senior undergrad project. So we've been trying to see how would planetary architecture affect the unbound population, right? Because we're looking so much at the Oort cloud here as the tiny amount of bound remaining objects. What happens to all of the ones that unbind? So the key thing that we really started to focus on was the velocity distribution here, because this is something where we do see a trend in both the ejected fraction here in the top left of how much of the disk that we put in is being ejected in that 10 megayear instability. And also we get a median velocity spread as well. So we are seeing some trends as a result of system architecture, the mass partitioning, these kinds of variables that you have in the planetary system, which is to a certain degree what you might expect, thinking about how you would need something very massive in the more outer part of that disk to particularly drive this. But we are seeing there is some trends around number of planets in the system and the planetary ejection happening as well. And if you compare this to the solar system, so in this lower plot, we've got Nesvorny here and collaborators 2024 kindly provided for us to compare with, looking at this over the time-sliced parts of that simulation of the unbound objects. We do see that the solar system, Nesvorny's one, of course, the simulation has a fair bit more physics in it than what we were trying here, but we are seeing some broad similarities. So in general, these objects are coming off their stars nice and slow. But what's happening to them after that? So at this point, we have to change simulation environments because, yes, as much as I'd love to say we have an end-to-end model that can do everything from planetesimal formation, unbinding, evolution in the galaxy, everything's in pieces at the moment. It is the way of things. So we unbind them. And then this is the point at which I really want to pick up on what the review talk was saying with the galactic potential yesterday. Yeah, we're in a galaxy. And as a solar system person, this has been a real evolution for me the last few years. Thinking first of, the dark matter and the disk as the background potential that's driving the more circular motion, the galactic shear. And then the structure of the galaxy, the kind of finer structure, is something that's driving the more stochastic heating aspects of this. So in terms of that, let's think about what's happening with the galactic shear for this. So this is a beautiful framework, and John's going to go into a fair bit more detail on how this comes together. But we're putting the particles for this framework. So if we say the progenitor, the origin star or cluster, is here, then we're putting the particles that have been ejected, say, for example, from Lear's simulations, into the Lagrange points. And we'd love some feedback if people think that that's something that we should try modifying or not. So from there, they can then evolve in the galactic potential. So over time, we'll go from left to right here in this. As you zoom out, you get a larger and larger grid. And so these are moving under that potential. So I guess this is, to a certain degree, kind of the level 3 that was being talked about yesterday, except this is kind of 3+A. So we're dealing in many ways with a sort of easier problem than what was being described. I also want to remind us that as the sun is happily doing its dolphin bobs around in the galaxy, we're getting a variation in the tidal strength. So as the sun is going through that, this cloud of loosely bound particles that are beyond what we typically think of as the Oort cloud, but in these Lagrange points, are experiencing a varying tide. And so you have these really interesting tidal developments happening. This is something John's going to give us a lot more detail on, but I want to kind of preview it for you with a semi-analytic approach. We can see this happening to a level of precision, right? So you can see the streams starting to develop in this top-down view of the galaxy. And each of these streams is going to have a very complex density structure. So to give you a quick cross-section of that here, it's going to depend where you're sampling on the stream, and it's going to depend how much heating some of these streams have had as well. So this is the behavior you get just without thinking about the additional heating things in the potential itself. But if I just change which screen I'm sharing for a moment, we can start to look at the case of what happens when you do add some heating. So this is work that Angus has been doing over the last little while. There we go. Yay, that should have changed accurately. So now we're looking at an animation where we have the one of these streams, and this is the case just with the ISOs that have been semi-analytically extracted in the previous framework that are now being integrated in the galactic potential. So the potential here is the BOVI 2014, the MW 2014 that is well known and loved. So you can see that this is showing a background of GMCs, but not actually applying any heating from them yet. If we then add heating to them, heating is now shown with the same stream, but being heated as an orange and the blue one there for comparison. So you now have the stream happily porpoising up and down through, but this now starts to raise an interesting situation where the progenitor is no longer at the center of the density distribution all of the time. Sometimes you get density clumps that are moving with respect to the progenitor within that stream. So between these aspects of density variation in the cross-section, density variation along the stream, density variation through time, we end up with a, I'm just swapping back to the, there we go, back to this PowerPoint. You end up with a situation where the question that I started being concerned by has been how much of, for the solar system, the one that we're encountering, how much of that is actually returning to us? So in this sense, I'm terming it a quasi-interstellar object, something that has unbound from the origin system, in this case ours, and is then re-entering the system. So in this case, it could have eroded off the Oort cloud in the recent past, or it could have left in the early dynamical instability. It spent time in the tidal stream, or to the degree of epicyclic motion that have been showing, and then returned back to us. So these are things that have not been parked in the Oort cloud, but they have in many ways been parked in our extended environment. So as an observer, this is where I started getting worried, was do we have a population that are now a foreground for our interstellar objects? So is this something where the interstellar objects that we would expect to see from the rest of the galaxy, from stream on stream on stream of the others, are actually having our own Oort cloud comets getting in the way? And that was terrifying, because then their physical properties are going to be the same as those that we see in the solar system comets, and then everything is going to get mixed up. And as an observer, that's a awkward situation to be trying to deal with, right? Because then the promise that we have for interstellar objects, that they can tell us about other stars through galactic history, is then potentially diluted. So this is something that we've been exploring. And one of the ways we've been exploring this is to switch to yet another model, is to think about whether we can debias the local stars to give us an idea of the local ISOs. So these are not ISOs that have come from these stars, to be very clear. These are ISOs that are feeling the influence of the galactic potential and its substructure in exactly the same way. So this makes the assumption that the ISO substructure will be the same as that of the stars. And maybe this doesn't always apply in the case of tidal streams. So if we debias these stars for metallicity...
We've got about 5 minutes left, so I just want to give you the time to make sure you've got time for questions.
Sweet as. If we debias this population for their age, their metallicity, the selection biases that Gaia has, you end up with an ISO velocity structure. And so this work has been led by Matthew Hopkins in his PhD, and you get these interesting velocity structure clumps. So we have some nice predictions about how this should be visible in LSST. Well, overall, you're going to see localized regions on the sky that you get interstellar objects coming in from. So some of these will be one-eye-like in velocity space, some of these will not. But if we think about where they're coming on the sky, we've known for a while, probably since the late 1980s, that we should have interstellar objects that have a preferred localization on the sky towards the solar apex. What we add in this work is the prediction that you would have these moving groups of ISOs also projected on the sky. And to summarize briefly the observational situation for that, we've not been looking in the parts of the sky at the right depths to detect these on their inbound trajectory. So Rosemary has some really nice simulations you should go look at and ask her about for what this means in LSST. But LSST's in the south. It sees objects both before and after their perihelion passage. So we do have a small survey that is running at the moment to start looking at whether we can see some of these objects with CFHT while they're still inbound. So this is the fun and also the promise and the worry of ISOs at the moment. We have a new field of galactic kinematics and small body galactic studies. But do we have a foreground from our own solar system that's going to be confusing? And this is something that I think John will have some more plots to show you in the next few minutes. Thank you.
We've got time for one quick question. I'm going to go with Colin.
I'm Michele. Can you hear me from here?
Can you give your name and affiliation just for everyone online?
Yeah, Colin, Snodgrass, University of Edinburgh. It's really cool. Do you see any difference in like velocity distribution for things that these quasi ISOs would be versus a true ISO coming from some other star? Would you, again, if you see enough of them, this is always going to be the problem observationally that we pick one thing. But do you see any difference population-wise in terms of velocity or anything else?
Our initial suspicion was that they're going to be coming in slower, which means we should be able to trim them off nicely relative to the faster ISOs that, for instance, we do see from the Gaia-derived population. But John has a nice plot or two to show you from that.
All right, we can take one more question. Anybody else? So I just had a quick question, Michele. So in terms of thinking about what the LSST can find, it sounds like more likely these things are going to be in the north. Well, we're not looking there. So is CFHT then the only asset that's going to be able to find them, or is there predictions that LSST, or is it that we need to have another wide field survey to actually discover an ISO? How pessimistic should we be about the LSST then?
I think we have predictions that we should be able to get now this will depend on the size distribution slope, but we should be able to get somewhere between 10 and roughly 50 ISOs out of LSST. So it's not as though we're never going to see ISOs with LSST, but we aren't going to see as many of them that are inbound as potentially we were thinking. However, this does get a little more complicated when it comes to the matter of tidal streams. So that's kind of the next level of refinement that we're looking at.
All right, well, that sounds like a good intro into the next talk. So let's thank Michele. And we'll bring on our next speaker. And again, if people have questions for our island speakers, I'm sure that they'd be very happy to take questions or inquiries via email. So our next speaker is John Forbes, and John's going to be talking about streams of interstellar objects. And I'll give you a warning when there's 5 minutes left in the session slot.
I'm muted. Okay. Can people hear me?
Yes.
Yes, thanks. Okay, so yes, this is very much a continuation on what Michele just introduced about interstellar objects and how we deal with them in collaboration with many people here at the University of Canterbury in New Zealand. I've highlighted some of the students and recent students like Rosemary here in bold. So Michele showed you this this movie, which I hope is showing up okay on the Zoom. This is an illustration of kind of our emerging picture of how we're thinking about the interstellar object population in the galaxy. Basically, rather than sort of a uniform background of interstellar objects, it's really a tapestry of streams. And this is a tiny, tiny fraction of those streams. Each star in the galaxy should be producing these streams. And if you think about it, even each cluster in the galaxy should be producing a stream of interstellar objects. And so this talk is about sort of how do we handle all these streams, or how do we begin to make sense of this? So Michele touched on this fact that in a lot of what I'm going to be showing you, rather than doing numerical integrations in the galaxy, I decided that it would be fun to do the integrations instead of by actually integrating, but not by actually integrating, but by just writing down the solution, which you can do, it turns out, if you know the potential and you're willing to use enough terms in your expansions. So this is based on the work of Lyndon Bell, 2015. So he basically came up with a very high order epicyclic approximation that lets you just write down the solutions to the location and velocity of particles as a function of time in the galaxy. So this is useful if you have a lot of particles, but they're not interacting with each other. And so if you, I just wanted to advertise this to this room because if you're interested in sort of how does the sun orbit in the galaxy, and you don't really want to spend too much of your brain power on that, you can pip install this this package LB Particles, and we have that for you. But anyway, so with this simulation, as Michele mentioned, what we do is we set up our streams. We have a progenitor particle here shown in blue, and we add in some ISOs at the Lagrange points in the galaxy. So the coordinate system here is the radius is up and down. So the galactic center is down at the bottom of the screen. And then this other coordinate is the tangential distance or the longitude around the galaxy. So we add in the particles at the Lagrange points, and we give them some finite range of velocities. And we see that they start evolving, and they do some very interesting things early on because they all are on essentially very similar epicyclic orbits. So the orbits are all very, very closely related to each other. And if you look carefully at one of these particles, it's sort of has this back and forth motion. And for this particular stream, if you let it go on long enough, it will begin wrapping around the galaxy. So the longitude here has stretched from its initial small value out to 180 degrees, and the stream is wrapping around itself. So, if you're worried about, does the stream intersect? Does the progenitor run into its own ISOs? This sort of indicates, maybe this is a possibility. What we call these streams awophiria, which are braided rippers in the Maori language, which are very beautiful and common feature here in the South Island of New Zealand. So we're big fans of how that worked out. So we have these simulations, we have these streams. How do we now work with this stream of particles and begin to understand how quickly how strongly they interact with various stars, and will we see them in sky surveys? So to do that, what we need to do is we need to take this set of points and be able to evaluate their density at arbitrary locations. And so this is a classic case where we kind of need a KDE, kernel density estimate. So we have these particles, and we want to be able to say at some arbitrary point where what's the density, and in fact, what's the full phase space density at that location. So with a KDE, usually what you do is you choose a Gaussian that's the same for all the points, and then you add them all up. And so at any given point, you just add up all the Gaussians, and the closer you are to all these points, the higher the density will be. But as you can see, when you have structures like we have here in like long thin streams with potential substructures within them, this is not the best approximation because you end up smearing out your fine details much wider than the inherent physical extent of the system. So what we did is so kind of just illustratively, what you kind of want is you want the Gaussians to kind of know about the other points. And so you want them to sort of respect the fact that the points really only lie along this line. And so what we do is we allow each point to have its own Gaussian, and that Gaussian is going to be some scaled version of the local. It's going to have a covariance matrix that's equal to some scaled version of the local sample covariance matrix. And so now, of course, we just made the problem very complicated because now we have a bunch of parameters that we have to deal with. We have to define what is n to figure out what the nearest neighbors are. What does distance mean? Because we need to know what nearest means. And we have this overall scale factor and an overall scaling with the determinant of this covariance matrix. So we have a bunch of parameters. The way we deal with this is cross-validation. So basically what we do is we generate a KDE excluding a fifth of the points at random. You evaluate the density using the KDE you trained on the 80% of your data with the 20% that you left out. You do that for all 5 folds of your data, and then you choose the parameters that gave you that provided the least surprise. So you technically you minimize the mean squared error or something that is an asymptotic approximation to it. So that's what we're doing when we try to understand the density distribution of these streams. So when we do that for these unheated streams, we get kind of actually a comprehensible result. So this plot is showing you, as a function of the density of the stream, what is the probability that you find a particle there. So these are normalized so that if you integrate over them, you get 1. So in other words, another way to think about this is, if you were to pick a particle at random from the ISO stream, what density would it live at? And what you can see is that for one of these streams, what happens is the density distribution starts here, and it's this nice gamma-like distribution, so an exponential with a power law cutoff, which other astronomers would call a Schechter function or something. And it just steadily marches to the left as the stream gets less and less dense over time. And the location of this peak density is you can understand it quite simply, actually. It's just 1 divided by the length times the width times the height of the stream, where the length is the velocity dispersion times the amount of time that's elapsed. The width is sigma over the epicyclic frequency, and the height is sigma over the vertical oscillation frequency. And so this means that essentially every aspect of the stream is being controlled by this velocity dispersion. So it's quite sensitive to the velocity dispersion. And on top of just this overall structure, you also get much finer structures when your stream is particularly cold, when your velocity dispersion is smaller than the scale of the epicycles. You can get very finely structured streams in addition to just this overall very sensitive overall being very sensitive to the velocity dispersion. So it's to us, you can really divide streams into cold streams and hot streams. So the cold streams are short, thin, and highly structured. And so observationally, this means if streams are cold, sun will be in fewer of them, but and the fewer streams there are, the more obvious their effects will be. So how do we actually calculate a rate? So what you should have in mind is, we're trying to predict what rate you see with LSST at a particular location in the galaxy. To 0th order, the rate is just the number density of ISOs times cross-section times the velocity, and the cross-section, because we care about the self-gravity of the sun, depends on the mass of the sun and the maximum pericenter that we're considering, and the velocity. Because of gravitational focusing. This is the gravitational focusing term. And it also, in detail, actually depends on the distribution of velocity. So you integrate over this distribution function, which again, we're estimating from the KDE. Then what we do to try to get a handle on all these streams is we are aiming to split up the streams by their rates. So we're going to get a distribution of streams as a function of the rates of encounters that we're seeing from them. So we're going to draw a velocity from the local stellar distribution function. We're going to draw some stream parameters, which we don't really know, but we'll give some guesses. And then we're going to draw the density from the density distributions, which we now understand. And then we weight the sample, and then we get this answer. So as a function of the rate of stream encounters, we get this number of streams. So what this is saying, and this is a cumulative distribution. So what this is saying is that there are sort of 1 million to 10 billion streams that the sun is currently in, but the vast majority of them contribute very, very little to the rate of ISOs. And I've highlighted a couple special points here. Oh, and I should say the dashed lines are streams from stars and the solid lines are the streams from clusters. So, you know, this point here near 1, I think I put it at half, means, you know, there are streams out here with very high rates, but because there's less than 1 of them on average, this means that those streams exist, but they're not likely to currently contain the sun. And streams over here that produce more than 0.1 ISO per year may produce duplicates in the LSST sample. And just a note that I've normalized all of these models to have the same total rate of 10 ISOs per year, which is you know, just a choice we made to put all the models on the same footing. Okay, and so as a result, as you increase your sample size, you are more and more likely to get siblings or cousins of siblings being ISOs from the same star and cousins being ISOs from the same cluster. And with a sample size of 100, you are likely to see many cousin ISOs, and maybe if you're lucky, sibling ISOs. Okay, so this all assumes that the ISOs are mainly coming from the early stages of the solar system. And so, you know, we know that of the planetesimals that you start off with in the disk, if you have a giant planet instability, the vast majority will be ejected and a small fraction will be left behind in the Oort cloud. And so if you ask what happens to these populations a billion years later, a few billion years later, the ejected streams will have run into molecular clouds, spiral arms, and so on, and they'll be heated or perturbed. Whereas the ones that are left in the Oort cloud may be gradually eroded by flybys and tides. And so they may be ejected much later and much colder. So each of these streams, even though they're most of the time will be hot, they'll have this cold core from continued erosion of exo-Oort clouds. So what this means is that ISOs may arrive from special locations because special locations where stars have recently had their Oort clouds eroded. And one way you can do that is by the variation in the tide. So this, for example, is the variation of the tide experienced by the sun. And this is the result of the sun crossing the midplane. So that happened a few million years ago. But it's also interacting with when the sun executes its pericenter in its orbit around the galaxy. So now here's the other question is, you know, if the sun is experiencing this variation in the tide, is that also eroding not just exo-Oort clouds, but the Oort cloud around the sun? So we set up an experiment to look into this. We integrate the sun's orbit backwards. We add at each time a burst of ISOs from the sun. And then we add some random motion to each of those ISOs. And so they're executing this random walk in velocity. And then we see what is the rate of quasi-ISOs that we get as a function of the time that we produce those ISOs. And so this is the answer. Yeah, good. Yeah, so just finishing up here. Yep, got it. So this is our best guess right now for how the quasi-ISOs work. So the red line here is cases where the streams are heated, and the blue line is the case where the streams are unheated. And so what's going on is that the heated streams are immediately isotropizing once they leave the solar system, and this is probably not realistic because, you know, the heating is shouldn't truly be a white noise process. But if you assume that happens, then the ISOs that were released a few million years ago will head back to us today, And you have a peak over here where ISOs are returning after executing an epicycle or a vertical oscillation frequency. And so if we look at one of these simulations, we see that it has these features in Y and Z of particles returning to the same location. Skip this density distribution. To answer a question someone asked Michele, the eccentricity distribution is very, very low. It's just barely above 1. So these are very, very slow, and they come in at special locations on the sky. And so let me just summarize now. So ISO streams and Oort clouds. Once the ISOs are orbiting in the galaxy, the ISOs form tidal streams. Streams are responsible for interesting things. So you can get multiple ISOs from the same star, special directions from which the ISOs will originate. The density and encounter rate per stream is set by the stream's velocity dispersion. The Oort cloud erosion is a continuous source of dynamically cold materials. So the Oort cloud erosion is cool, just like the galaxy. And our predictions for Rubin are that, we'll find of order 1 quasi-ISO, maybe 1 ISO from the same star as another ISO in the sample, and maybe 1 to 10% of the ISOs will share a common birth cluster. So that's it for me.
All right, we'll start here for questions.
Giovanni Valsecchi from National Institute of Astrophysics of Italy. I am struck by the analogies that I see in your descriptions of these tidal streams with the type of analysis that is done to study the formation and orbital evolution of meteoroid streams in the solar system. You have epicyclic motion afterwards instead of having Keplerian motion, but the ideas seem to be analogous at least. And another analogy that strikes me is the one with the Earth re-encountering spent spacecraft that had been sent on heliocentric orbits. I think already there have been 1 or 2 cases of past spent spacecraft mistaken for new asteroids with very low speed. Anyway, it's a comment, it's not a question.
Al.
Hal Wilson from Southwest Research Institute in Boulder. Has anybody looked, well, let me take a step back, right? The solar system is currently going through stellar association centered on Ursa Majoris, right? There's stars that are part of the stellar association that are all around us. These are stars that are currently unbound but have the same velocity through space. Has anybody looked at the idea that a lot of the interstellar objects that we might see are associated with this stellar association?
Yes, in fact. So we were inspired in part by this paper by Simone Portuguese-Fart in 2021 called Oort Cloud Ecology 1, where he took the 200 nearest stars and made predictions for their ISO streams. And in fact, he saw streams coming from them. Our prediction is that that's going to be, the 200 nearest stars are going to be pretty minor in terms of their contribution, and the vast majority of the ISOs will come from much further away, possibly sort of all the way around the galaxy.
Oh, that's interesting.
Pedro.
Pedro, University of Coimbra. This is also for Michele, if she's still online, or for you, John. The 1I and 2I are really, really different. And on trying to distinguish these quasi-ISOs from real ISOs, I mean, this sort of, now not looking so much at the dynamics, but at how they look like, is probably also a good way to tell which are which, right? They're more different than anything we found in the solar system, almost.
Yeah, certainly. Although, I guess you could worry that the fact that they've left the solar system could expose them to a somewhat different environment, but maybe not. That's not such a big worry for the outer Oort cloud. But yeah, I mean, I'm pretty optimistic that the velocities will really distinguish the quasi-ISOs from sort of the true ISOs, but it may be difficult to distinguish quasi-ISOs from long-period comets.
Yeah, I agree with that. I think With 1i and 2i, I would be very surprised if they count as quasi-ISOs, because even when you compare them to the property distributions that we have from the solar system, they are extremal. So a prediction of quasi-ISOs as a concept is that they would be well within the property distribution that we see for LPCs or anything else like that, right? The well-understood solar system populations. So they should be more physically similar. Yeah, I think that's probably where we're, and also the velocities for 1i and 2i matching the moving groups that you see in the Gaia data is suggestive.
All right. We'll thank our speaker and on to our next topic. And now for a change of pace, we're going to talk about missions or future missions. Colin Snodgrass is going to talk about ESA's Comet Interceptor.
Okay, yeah, so let's talk about Comet Interceptor. To start with, we're going to start thinking about comets as geological objects and things rather than test particles. These things are actually solid bodies with shapes and properties and all sorts of things going on. And these are the ones we've seen with space missions so far. And obviously, if you get a space mission to a comet, you get a lot more detail that you can get from telescopic observations. You can actually get the resolved shapes like these of the nuclei. You can look at where their activity is on the surface. You can measure composition directly rather than inferring it from spectra. You can look at how they interact with the solar wind and so on. But what all of these comets have in common so far is that all the ones we've visited so far are short period comets. And that is for the very good reason that if you're going to plan and build a space mission, this generally takes decades, and that you want to know where you're going to start with. So you go to a comet where you know the orbit and you can actually plan this. All of these missions have been fast flybys apart from the Rosetta mission, which is the rendezvous one. And again, this took 10 years of orbiting around the solar system to rendezvous with a known orbit. So the difference with Comet Interceptor is this is the first time we're going to try and target something that's a long period comet. Possibly an interstellar object, but most likely this is something coming from our own Oort cloud. And the point of doing this is to go and see something that hasn't gone around the sun many, many times in the inner solar system. So all of the previous ones that we've seen have very evolved surfaces. And one of the main things we found from Rosetta is how much of the dust is falling back as well as escaping out into the coma. There's large deposits of material that is lifted and fallen back. All the surface has been eroded and then grown in other areas. So what you're actually seeing with in these nice images is not a surface that was laid down at the beginning of the solar system, and the way that we like to think about comets is these really pristine objects. Now, we know that a long period comet is also going to have had some sort of evolution, particularly in the earlier solar system, but relatively, these things are going to be more pristine. It's the argument for Comet Interceptor. They're looking at something, particularly if it's dynamically new, that has not seen a lot of solar heating in the past giga-years timescale. And so you're looking at a surface that is relatively unaltered. But as I said, the challenge with a long period comet mission, the reason why so far we've just done short period comets, is that the only way you can encounter a long period comet is to discover it inbound when you've got enough warning time to actually find its trajectory, get a spacecraft into the right place to intercept it. Mostly the comets we're actually discovering are actually only as they're coming into the inner solar system, historically within sort of 3 AU or so. Now we're going and finding them sort of out to kind of beyond 5 AU more regularly. But that's still only kind of months to years from perihelion passage. So that's no time to kind of plan and build a spacecraft, and it says on decades time scales it takes to get a plan together, get it agreed and funded, build a spacecraft, launch it, etc. Hopefully what with LSST, we're starting finding these things regularly out at kind of 10 AU or beyond, and this gives us kind of years warning time rather than months, which is still not enough time to plan and build a spacecraft and get it to a specific object, unless you're very lucky and you discover these things very far away. But it does enable the mission because it gives you enough time to at least reach it if your spacecraft's ready. So the solution for Comet Interceptor is that we build the spacecraft to go to a generic comet, we launch it into space, and then we loiter there and wait until we get a comet that we like the look of, that we can reach. And so the Comet Interceptor concept is that we launch to the Sun-Earth L2 point, and we can have a halo orbit around the L2 point with station keeping there with relatively little fuel, and then you're in a good point to then, when you find a comet that you like, depart L2 and go on to an intercept to meet a comet somewhere near to Earth's orbit, and then we can find a comet coming in, and with sort of 6 to 12 months warning time between discovery and departure is enough. You then need a couple of years, potentially cruise time, to get there. But this means that if you're discovering something a few years out, that's enough time to get the spacecraft there. Okay, so this concept is we proposed as the first F-class mission for ESA. So F-class initially meant fast. I think they then said it meant flexible. Neither of these things are true. But the idea with the F-class was that this was sort of a mission of opportunity. It was they realized that there would be some ride-share potential with the Ariel mission, which was going to go, it's an exoplanet space telescope that's going to go and park at L2. And so there was a call for relatively small scale missions for ESA to share that ride and to make use of this launch. And so this thing is, budget-wise, is a kind of 10% Rosetta. So it's a much smaller scale thing than ESA's previous Comet mission. But this is, it fits well with the concept here. This is one of the reasons why we won this call, is that this works well with a ride along to L2, because that's a good place for us to park. Currently, we're actually looking at other options for a rideshare, although it's designed to have launched with Ariel. There are some concerns about the Ariel timescale, and ESA is looking at other options for us to launch instead. Okay, so this is the kind of sketch of how the idea works. We launch nominally with Ariel to L2. We go into this halo orbit around the L2 point, and then we can wait there for up to a couple of years. The timescale is largely driven by the 6-year timescale of the whole mission, which is driven by budget. We could, potentially wait longer. There's no reason from the spacecraft point of view. Anyway, we hang around out there. Meanwhile, LSST is scanning the skies, finds us a comet that looks like it's going to be a good one. And by a good one, we mean that this thing is going to come and cross the ecliptic plane somewhere near 1 AU. Because we're a small mission with relatively limited fuel and relatively limited delta-V, so we can essentially reach comets that have a plane crossing close to 1 AU, between about 0.9 and 1.2 AU. So we have this kind of annulus reachable space. We find a comet, we find it, project its orbit, we say this is going to cross the plane somewhere near where we can reach. We think that this is otherwise a good comet that we like the look of. We then leave L2 to get ourselves to meeting the same point in the ecliptic at the same time as the comet does. And then we're going to have a fast flyby encounter as the comet crosses the ecliptic plane. So it's more comparable with Giotto or any other of the other flyby missions to comets than Rosetta. It's as I said, fast flyby on this sort of budget scale, and also with a long period comet orbit. Matching orbits is not going to be a realistic thing to do. But what is new and what's quite neat with Comet Interceptor is that we're taking multiple spacecraft. So we have a main spacecraft which is going to have a flyby at around about 1,000 kilometers, maybe a bit closer, maybe a bit further, depending on the activity level of the comet, which is somewhere which is a relatively safe distance for in terms of the dust environment for a high-speed flyby. But then we have two smaller spacecrafts that are released just prior to the flyby, a day or a couple of days out, that will be targeted to have a much closer encounter going through the inner coma. So this is partially because this allows us to have, the main spacecraft relatively safe and the small spacecraft are expendable. But also this is quite a nice thing scientifically because it lets us have multi-point measurements within a cometary coma. You can see what variation, if you measure different, composition or different properties in different places in the comet. Is this because there's some intrinsic variation in it, or is rather than some time varying measurements? One of the things with Rosetta, we had a single spacecraft, and if you were measuring a different composition on one side of the comet, by the time you've got round to the other side, this has taken days to weeks, depending on the mission phase and the orbit, and you're measuring differences there. Is this a time variation, or is it just intrinsic variation in the comet? So these multi-point measurements are quite a nice feature, as well as enabling us to have different distances from the comet and different risk profiles for the different spacecraft. Okay, so this is a little sketch of our three spacecraft. So the spacecraft A, this is the main thing. We actually get the highest resolution images from the imager on the main spacecraft, because although the other probes go closer, the main spacecraft is where we have kind of larger, bulkier instruments, and including COCA, the high-resolution camera, which has got decent optics for giving us kind of 10-meter resolution-ish images from 1,000 kilometers off. I'll go through the payload in a little more detail in the next slides, but essentially, we have a main spacecraft that also acts as a relay for the two probes that are released and are then sending back all the data they're collecting in real time. They are designed to be expendable. They are meant to last hopefully up to at least closest approach and a bit beyond. But they are not expected to survive the encounter, particularly the B2, which goes closest, and it's just on battery power. So it has a limited lifetime in any case, whether or not it meets any dust grains that are a bit large for its shields. Okay, payload, a little more detail. So as I said, the COCA is the main camera on board. It's actually based on the Cassis instrument on the ExoMars. So again, this is got an actual proper telescope on this to give us decent resolution from a safe distance off. We have a mass spectrometer, which is based on the one that was on Rosetta, on Rosina. We have MIRMUS, which is an infrared camera. It's actually a 3-channel thing through near infrared through thermal infrared. And this is going to be quite interesting. It's the first time we'll have had a thermal infrared camera at a comet, so that's quite nice in terms of looking at the actual properties of the surface and what's driving activity. And then we have many instruments squeezed into one instrument in terms of not scaring ESA with how many things we were going to pack onto this instrument, onto the thing, which is dust fields and plasma package. So this is the various sensors that are, dust impact detector, and then also looking at the magnetic fields and plasma and composition and electric field, ions and neutrals, etc. On the B1 spacecraft, so this whole spacecraft is actually provided by JAXA. So the main spacecraft and the other probe are all European, but this is a collaboration with the Japanese, and so JAXA provides the B1 spacecraft and the payload on it. It has this far UV camera, the hydrogen imager, so this is looking at Lyman alpha, and it's looking at the whole coma from this, and it's actually going to get us water production rates and also can measure D2H. It's a very small camera, but it's quite a neat thing. They also have a plasma suite on here, another magnetometer. The magnetometers are the only real 3-point measurements. It's the only instrument we have on all 3 spacecraft. And then it also has a couple of cameras, including, and I love this, the narrow angle camera on the Japanese spacecraft because the spacecraft will maintain a fixed attitude relative to ram direction as it goes through the coma. It means that its narrow angle camera isn't tracking the comet, and actually the comet will be within the field of view of their narrow angle camera for 1/4 of a second closest approach, during which time they think they'll get 2 or 3 images. This is gloriously crazy, but I love working with JAXA. B2 spacecraft, this has an interesting thing with it has a polarimetry instrument that is going to scan the whole sky. So the B2 spacecraft is spin stabilized. We said it's spinning and throw it like a dart. And the NVIS camera looks out one side with a fisheye lens to get you kind of 180-degree stripe that then sweeps around the whole sky as it goes around. So this is going to be quite nice because it's going to be within the coma and it's going to be measuring the dust properties via polarimetry, all phase angles, all the way to looking at the sun, all the way to anti-sun, as well as getting some nucleus properties as it goes by. We also have this miniature camera with a periscope to look forward past the dust shield, just for monochromatic imaging, and then again parts of this dust field plasma package, the magnetometer and the dust impact detector on the small spacecraft. Okay, this is more or less how we work in the flyby. As I said, the main spacecraft kind of stands off and has a distant flyby, but actually returns the highest resolution imaging. Pardon me. While the 2 small spacecraft go much closer and are constantly transmitting their data back. Most of the operations of small spacecraft are quite limited by this intersatellite link. That's the data rate is going to be one of the really key things that we're limited by there, as well as the limited lifetime of these spacecraft.
We're at 5 minutes including.
Okay, thanks. And so, yeah, they transmit data back to the main spacecraft. The main spacecraft is then going to transmit data back down to Earth over months after the flyby. Okay, so there's some challenges with this. We don't know where we're going. We don't really know how the rocket works. They have now launched an Ariane 6.2, so it has been tested slightly. How successful the first test was depends who you ask, but it has at least flown. How much mass we actually have is still an unknown thing until Ariel's actually finished being built, because they're prime, and so we're kind of like, you can do with what's left over. So we end up with a very large uncertainty on what our delta V capability is, because essentially this is most of our mass uncertainty is going into fuel. So we've got oversized tanks on this, and essentially we'll top it right up as much as we can once we can finally know how much weight we can put in the rocket, and more fuel is better. Pardon me. And more fuel is better because essentially the longer warning time we have, or the more delta V that we have, the larger part of this annulus around 1 AU we can actually reach. So if we're very lucky, we get a comet that's actually coming relatively close to Earth, and then we have a short cruise, and we have plenty of options for the encounter. If we're unlucky, this thing is, right around the other side of the sun, which is not an encounter we would like to have, but and also would take much longer to get there. Okay, and then so finally, where are we? We are building hardware, basically. This thing was selected in 2019, went through the sort of formal approval, adopted in ESA speak in 2022. And then, yeah, currently they are building bits. The instruments get delivered late this year for the B spacecraft, early next year for the A spacecraft. Here are some photos of some actual hardware of people making things. And then meanwhile, yeah, we're working on target selection. We're working on planning for everything. Should launch 2029 or possibly slightly earlier if we're going with Ariel in the end. And so mid-2030s for a Comet flyby. All right, stop there and take any questions.
Any questions?
Julio Fernández from the University of the Republic, Montevideo. There is, I think that a crucial problem will be just to be sure that you can detect the nucleus of the comet, because I am worrying about the optical depth of the coma. if the comet is very active. I think the only way that I see to solve this problem is just to approach the nucleus almost in a suicidal trajectory, just to destroy. But maybe you have to moderate the distance of closest approach to friends. I can go down to, I don't know how much you can decrease the distance.
Yeah, we can vary it depending on the activity level of the comet. So the 1,000-kilometer flyby is based on our kind of Halley-like encounter. So basically based on what they did for Giotto, which was, I think, 700-ish kilometers. The idea is that they more or less survived with Giotto, and so with similar shielding at a similar level of activity comet, a 1,000-kilometer flyby is seen as safe by the engineers. Now, the chances are the activity level of the comet is maybe not going to be as high as Halley, in which case maybe we can go a bit closer, or if we get something that's really high activity, and we can go a bit further away. You're trading resolution you'll get with the cameras. I don't think the optical depth is too much of an issue. The optical depth of a cometary coma is normally pretty thin. You know, they saw the nucleus fine with Halley from these kind of distances. But yeah, the main question on how close or how far we can get away is going to be the activity level plus the encounter velocity. So if we end up with a very high-speed encounter, if we get something that's very retrograde comet, that limits us more. If we get a lower speed encounter, then we can get closer because you've got some limits on the angular rate of motion of the tracking mirrors that are going to actually track the nucleus as you go by. The spacecraft keeps the same orientation to keep dust shields forward, and then we track. Yeah.
All right, I think we will end it there because we're eating into the coffee break.
Yes.
All right, so let's get started for the second session in the morning. So we have Hans Rickman, who's going to be talking about whether Ariel can detect the effects of exocomet showers on exoplanets.
Yes, thank you. So the two colleagues of mine mentioned here are colleagues of mine in the Ariel science team. So we started discussing this idea a bit. And what about the ubiquity of Oort clouds? I don't know how many of you have been thinking that most of the more or less sun-like stars in our part of the galaxy are equipped with Oort clouds. Raise your hands. Okay, yeah, a fair fraction. Well, I should raise my hand as well. Because we really can't say much at all a priori about this question. But there are a few things that we can note. For instance, that the scattering of planetesimals by giant planets or their cores may be a necessary outcome of the giant planet formation by core accretion. I think that's very natural to expect. And if we have planetesimal scattering, that would necessarily lead to Oort cloud formation, either via galactic tide or field stars and possibly birth cluster effects. So it's very natural, at least, to believe that Oort clouds should be ubiquitous. Okay, we don't know. So how can we find out? So Oort clouds maybe should be ubiquitous around the host stars of exoplanets. And they would also be, well, sources of interstellar comets, as we have heard. And so we looked a bit into whether, well, what we can say based on general arguments, and this is first about comet showers. If we have an Oort cloud, we have comet showers, so exoplanets around host stars having Oort clouds, they will experience comet showers. That's natural, very natural. And I show you a picture from a paper by Marc Fouchard, myself, Christian Froeschlet, and Giovanni Valsecchi, more than 10 years ago. We were called the Gang of Four in those days. So we published a few papers about the history of the Oort cloud of our solar system. And our simulation results showed us that the frequency of major comet showers from the Oort cloud would be of the order of 1 or 2 per gigayear. The duration of each comet shower is estimated to be a couple of million years, right? So from this we can deduce that about 0.5% of the time is spent in comet showers for a typical planetary system with an Oort cloud. Now, so that means that, okay, I will get back to that in the next slide, but let's keep this in mind, 0.5% of the time. If we have planets like hot Jupiters, or like the typical transiting exoplanets that Ariel will investigate, typical semi-major axis is of the order of 0.1 AU. So from that, we can expect to have of the order of 40 orbit crossings per year during those showers. So during a shower, we have this number of orbit crossings by comets per year. Then taking into account the cross-section for an impact onto a hot Jupiter or just a super-Earth, we find that the typical impact interval during those comet showers would be of the order of 5,000 years for hot Jupiters and about 500,000 years for super-Earths. Yeah, so what can we say then? Tentatively, if exo-Oort clouds are indeed ubiquitous, out of the about 1,000 Ariel target planets, a few of them would be expected to statistically be undergoing a comet shower right now. Just a few, but it's better than nothing. Among those exoplanets, a typical hot Jupiter should have had its latest comet impact like a few thousand years ago. For super-Earths, we would expect a few 100,000 years. So those are long times. And then we come to questions about the detectability of such comet impacts. Now, hot Jupiter impacts, this is SL9, the impact spots on Jupiter shortly afterwards. Those disappeared in a short time, and now in order to say something about how likely it would be to see the traces of such impacts if they happened thousands of years ago. Okay, we take a comet mass, like for the Rosetta Comet, 10 to the 13 kilograms. We have an impact speed, which is the combination of an approach velocity so close to a solar-type stars, it would be like 100 kilometers per second. And the escape velocity from Jupiter is like 50 kilometers per second. We combine those to have an impact energy per comet of the order of 6 times 10 to the 22nd joules. And that's similar to the energy of the KT impact, just for a comparison. But the question is, where is this energy released? The comet plunges down through the atmosphere of the giant planet, and it breaks up at a certain point, and we have an ejecta plume rising from this point of explosion, of energy release. And I don't know how deep this is, but maybe one should try to find out. There may be something we can say about it, and I don't know what, but we have a scenario where we have this impact plume rising from a point somewhere in the atmosphere relative to the cloud layers. I don't know where, but the question is if we can detect the cometary material from this impact plume thousands of years later. If we look instead at super Earth, well, we can take the analog of the KT impact on Earth, and the energy is of the same order again. It's like the KT impact. And let's not worry about biologic mortality and things like that, but there will be a heterospheric mass loading. That is, the super Earth has an atmosphere with a homosphere and a heterosphere, and the upper layers, the heterosphere, that's where you can dump lots of cometary material in the form of decomposition products of cometary organics. And they will last longer. How long, I don't know. And that's a critical question to answer. But there will be a sort of alien pollution by cometary material in those heterospheres of super Earth planets, and also the outer layers of hot Jupiter atmospheres. Now, those will be chemically distinct from the normal gases of the planetary atmospheres. And the question is, when Ariel takes transit spectra of those atmospheres, would it be possible for Ariel to detect those cometary materials? So here we have a number of important questions to try to answer. What is the expected structure of Oort clouds as a function of age and how they were formed, what was the primordial planetary system like, and so on. So we can look more closely into that. And what is the likely range of impact frequencies during comet showers? I mean, I just gave you a few guesses from the top of my head, but we can work more on this. And where is the site of terminal explosion for hot Jupiter impact? How high does the plume reach? We should be able to study this better. And what amount of cometary material is dumped into the super-Earth heterospheres? And very importantly, what is the lifetime of observable pollutions? As time goes on, those chemically alien species will undergo reactions, photochemical reactions and so forth, which may wipe them out after a long time. How long time? I don't know. But what shall we do? Well, we can estimate the chances of Ariel observable effects on planets undergoing comet showers. At least one thing that we can try to do. But independent of this, the Ariel transit spectra will be available at no cost. It's the usual Ariel observations. So why not look at the spectra? So thanks for your attention. Questions?
All right, we'll start with Morby.
Morby from Collège de France. Just a comment about whether Oort cloud are ubiquitous or not, because I think this is interesting. You may be right, but maybe not, in the sense that a characteristics of our solar system is that the giant planets are distant, so when they became unstable, they could scatter the entire planetesimal disk. But how generic is that? We really don't know from observations, but we know that planet migration is a process that typically works and brings planets closer to the star. And if this happens, then the distant planetesimal disk becomes detached from planets and stays there forever. This is how we observe debris disks that last hundreds of millions of years. And the planetesimals closer to the star, where the planets go, are not ejected because the Safronov number changes. They are rather accreted rather than ejected. So it's not so obvious that every star has Oort clouds. And it really depends on how ubiquitous is planet migration.
Yeah,
I would say.
thank you. Yeah, I agree.
But during the migration, they can count.
But there is
things.
gas during the migration. So maybe you form more clouds of big objects only, and not small bodies.
We're going to go Thomas Quinn.
I'm going to continue on a similar vein. It's also the size of the planets, right? So if we had Jupiter, right, that is the trapping efficiency is going to depend on the orbital architecture of the planetary system. So like big planets, trapping efficiency is going to be low, and so the comet shower flux is going to be low. If it's just all super Earths or whatever, mini Neptunes, then it's going to be the other way. You're going to have showers all the time. So the trapping efficiency is high.
Bryce.
Bryce Bolin from Eureka Scientific. So let's say, for the sake of argument, that we all agree on a universal definition of what an Oort cloud is, what outer Oort cloud is. So let's say for planetary systems which do have some kind of Oort cloud structure, whether it's inner or outer, which would we expect to be more common? Outer Oort cloud-like structures or inner Oort cloud-like structures?
Yeah, well, the comet showers that Julio will talk about, they arise from close encounters where the inner core is activated, so to speak. So if we have young Oort clouds which simply consist of an inner core without an outer halo, I think we will have the comet showers anyway, perhaps even more recently.
Any other questions? Colin?
Yeah, briefly, Colin, Snodgrass, University of Edinburgh. Yeah, it's worth remembering that by definition, the Ariel targets are all things that have got big-ish planets in very close. So they have had migration that's got hot Jupiters and so on. So following on from Morby's point, I don't know whether or not you get systems where you have things where you get a hot Jupiter comes in, but you're still left with things further out. So yeah, it might be that you're, by the fact that Ariel is observing things that have very, big planets close in, you're selecting systems. We're biasing it against Oort clouds.
I'll take chair's prerogative to add a question comment. But then also, if you think that most planetary systems form an embedded, or stars form embedded clusters, could you not then go with the Leveson sort of model of stealing an Oort cloud, right? Because you're getting it from the cluster, right? So that it wasn't yours. It's everybody else's contribution making yours. And so then could you have systems like STIPS closer inward, but actually that Oort cloud comes from the mechanism that Hal has proposed?
Depends how many stars you check.
Yeah. And one more.
Tomek Wiśniewski from Space Research Center, Poland. I have a question, or rather a comment, concerning the chemical distribution of organics in the atmosphere, because there are many sources of organics. For example, outgassing of the planet can cause that we have a real zoo of organics in the atmosphere. In such case, an addition of organics compounds from the comet will be very hard to detect.
So you're talking about so terrestrial-like planet in that case, not a hot Jupiter. But yeah, it's one thing to look at. If one sees something in the spectrum, could it be volcanically produced species or not? Okay, that's worth thinking of. Yeah.
All right. So I think we'll leave it there and move on to our next speaker. So that will advance, that will laser, we put that and then focus it on here.
Okay.
And this will advance the other way. So today, it's my pleasure to introduce the last talk before lunch. It's between you and your meal, but it's going to be a good talk, so this makes it worth it. So Julio Fernández is going to tell us about comet showers, their relevance, and the impact history of the Earth and other planets. And I'll give you a warning if you're still talking at the 5-minute mark in the session.
Okay. Good morning, everybody. Well, already Hans and Tom have referred to comet showers. I'm going to talk a little more about the possibility that comet showers occur. Well, first of all, we start with the beginnings. That is, how do we know that we have an Oort cloud? The main observable is the distribution of orbital energies that show a spike in a very narrow range of orbital energies that is represented there for this by this variable x, that is the reciprocal of the semi-major axis, in these strange units, 10 to the minus s AU to the minus 1. And then we can just point that there are two, this is a spike, and there are two secondary peaks at these values in the x units. And one important thing that we learn from the distribution of orbital energies, there are very few, we observe very few comets with original energies positive. That is, that would indicate that they are coming from the interstellar space. Then we can just conclude that most the Oort cloud are comets bound to the solar system. Well, this is the picture that I have already presented by other people here. And then we can define the classical Oort cloud that has energies in this range between 10 and 100 in these units that I defined before. And then the question is, of course, is the classical Oort cloud, that is is a part that we can observe, has an inner core. I will refer to this later. Well, let me just take a concept borrowed from Fouchard and colleagues, chambers and creepers. These are the two classes of Oort comets that we can define. Their chambers are the ones that can overshoot the Jupiter-Saturn barrier in a single revolution, and they have orbital energies weakly bound to the solar system, and they have the creepers that they have orbital energies a bit stronger, and they need several steps in order to get to the inner planetary region. And then we have as a hypothetical structure is the inner core of the classical Oort cloud. Well, then we can estimate the population of the Oort cloud, taking into account the observed rate of comets that we can observe coming from the Oort cloud, what we can define as new comets. That is a combination of jumpers and clippers. And we have this, we come here to this value that is easy to remember as 3 new comets crossing in Jupiter crossing orbits, from which about 43% are jumpers and 57% are creepers. Well, and then we're going now to just to discuss why the Oort cloud should have an inner core. Then the first thing that we have to take into account is that comets are well formed in situ. That is, the model showed that comets had to be formed in a region where the density is high enough in order to form planetesimals, and then we need to form the planetesimals or cometesimals in the planetary region, and then the formed planets just scatter the planetesimals to larger distances. The problem that we have in this case is in the current galactic environment, comets will be trapped in the Oort cloud, but not in the core, because they will continue because perihelion distance are not detached from the planetary region. They will continue passing through the planetary region and get scattered after several revolutions. Then how can an inner core be formed? This is the question there, and then the answer is that the Oort cloud formed in a different galactic environment. And this is just not a theoretical construction. We know that really most stars, or almost all stars, form in open clusters like this one. A model shows that when you have a formation of the Oort cloud in a galactic environment in an open cluster, depending on the density of the open cluster, you will have different structures of the Oort cloud, from more loosely bound comets to very compact clusters with a very, very heavy, very massive inner core. In the case of a dense, a large open cluster. And then there are some models that show that comets scatter from the planetary region, distribute with the heliocentric distances in this way, with a density of comets that falls with this power there. And then from these models that come out from numerical simulations, you can come up with an estimated population of the Oort cloud, and they take into account also the observed flux of comets, or the population of jumpers that we observe in Jupiter crossing orbits. Well, then what we know from what we know about the inner core? Actually, we have, I would say, 3 or 2 objects that could be members of the inner core. That are Senna and BP 113. There are a third one that is very doubtful because it has a perihelion distance smaller, and we know from the cosine mechanism can rise perihelion distance without the need to have stellar perturbations up to 70 AU. How people already have mentioned that in previous talks. And then other thing that we have to talk about is about what is the possibility to have a close encounter with the sun. Then if we take into account the star density in the solar neighborhood at present, is this one, then we come up with the result that shows that there should have been about 150 passages of a star within the inner core during the solar system lifetime. And that gives a minimum distance of approach to the sun of about 100 astronomical units. And that 100 star passages implies that one passage every 30 million years. Well, then we have that the Oort cloud, because of the different external perturbers, the galactic tides and passing stars have been thermalized, and that implies that the vectors are randomly distributed, the velocity vectors, and except for distances smaller than a certain value, that implies q distances smaller, the comets that enter into the inner planetary region, and then we know that once that they enter into the planetary region will be removed from the Oort cloud. These comets with this value here, q smaller than a certain qp, that is more or less the value of the radius Jupiter, the radius of Jupiter orbit, that will be empty. That is, there will be no velocity vectors for these values because they just are scattered, these comets. And then we have a loose cone. There we have a solid angle of this value, and we have the solar direction as the axis. And then this will more or less the geometry of a star encounter in the inner core of the Oort cloud. Then we have here a star passing, and we can assume in a first approximation that the star is rectilinear. And then we have that it passes a certain distance of a certain comet C, a distance t, and to a distance t sun from the sun. And then we can compute how many stars will be perturbed within this trajectory. It's a kind of tube. And what is important, we are not going to the details, but what is important is that the comet density, that of course is unknown in the inner core, and we have to assume that a certain value for this. Then we have certain here some results, numerical results taken as an example. That is, we just take into account the estimated population of the Oort cloud. We extrapolated this population with this law r to the minus 3.5 to the inner core. Then most of the comets will be concentrated in the inner core of the Oort cloud. And then we have a star passage there. And then we have different passages with minimum distance that are indicated here. And you see that as we consider a star that pass closer and closer to the sun, then we will have more peaks of comets that are injected into the planetary region. And then for different passages or closest distance to the sun, we will have, this is as a reference, what is estimated background comet flux. That is, we mentioned before, about 3 comets in Jupiter crossing orbits per year. And then we have different distances to the sun. You know that it could be as high as, for closest distances of 100 astronomical units, several thousands of times greater than the background comet flux. Then it's quite considerable. Well, now we are going to the question. 2 comet showers reflect in the impact cratering record. And we will take the example of the closest encounter to the sun. That is, we assume that a star that is passing to 1000 AU from the sun, and then we will have, we can make some estimate, and we come up with that result. There is only 0.1 impact craters produced by this shower. And why is so low? Because the probability of collision of a body coming in a random orbit with a random inclination is extremely low. And then it doesn't matter that the shower is very intense, but the collision probability is so low that the actual collisions are very, very low. Then when we compare with the rate of impact craters produced by asteroids, then we see that asteroids are the ones that dominate the cratering rate. Then it's irrelevant. Even the most intense comet showers that don't have any mark in a footprint in the impact cratering record. Well, this is the conclusion. And then we have to go. There is another way to observe shower that occurred in the recent past. Okay. The other thing that we can analyze is that the star will pass and will just produce a streak of the aphelion directions of the comets that will be noticeable on the sky. And this streak, if we can observe one of them, will be an indication, a clear indication that a star passed very close to the sun and produced a comet shower. This is a simulation, again, at different distances to the sun. And what are the results? What are the problems? Well, let's go. What are the question is then, what are the chances of observing one of these clusters in a present? Well, then we have some quick calculations. Time scale for close encounter of the sun with a passing star at this distance, we just mentioned before, was about 30 million years. The time scale for dissipation of a cluster, a comet clustering, is less than 1 million years. Then the probability of observing a clustering caused by a stellar passage is very low, because it's less than 1 million years in a time scale of 30 million years. This is the conclusion. Is there another way of looking for comet clusterings caused by star passages? Well, the answer is quite optimistic. Yes, there is another chance, but we have to observe comets that are coming not so close to the sun. for instance, comets producing a shower with perihelion distances that are beyond Saturn, because the comets will be perturbed less by the planets and will remain for longer times. Then the clustering will last for times that it could be 10 or 100 times longer. What is the problem right now with this observing comets so far away that we really we have discovered very few of them. Here we have comets with the greatest perihelion distance have been so far been discovered. You see there are very few that have perihelion distances greater than 10 astronomical units. We need to improve the sample in order to observe the distribution of the perihelion distances in the sky to try to detect streaks produced by recent comet passages. And then, for instance, the LSST survey could give the answer to discover enough comets in this region in order to have a sample large enough to detect a concentration of aphelia in the sample. Well, then we shall come to the conclusions. Well, then what are the points to be stressed in this talk? Then, first of all, that the formation of the inner core of the Oort cloud is a consequence of the formation of the solar system in a dense galactic environment. Then the other important fact is that the occurrence of close encounter within the inner core, defined as this region with radius of about 10,000 AU, and this is about once every 30 million years. And then the other conclusion is that these passages can trigger comet showers, but of course the intensity of the comet showers will depend on the density of comets in the inner core. Then will be hopeless to try to detect comet showers in the impact cratering record, because the impact cratering record in the Earth is dominated by asteroids. This is the other conclusion. If we go to the observed directions of aphelion points and to try to detect the streaks that will leave the star passage, the problem will be that for comets in Jupiter crossing orbit, that is that we observe now in the great majority of the comets are in Jupiter crossing orbit, this streak will be short-lived and then difficult to observe one at present. And then we have to go, and this is for the near future, to try to get a sample of new comets with perihelion distances in the region of between Saturn and Uranus. And there we will be able to detect if the comet showers occur, these streaks of aphelion points in the sky. And the last one.
So you got plenty of time for questions. Okay, see you hands in the back, so start there.
Yeah, hi, I'm Johansen from University of Copenhagen and Lund University. I was wondering, when you define an impact and you compare a comet to an asteroid, but a comet of the same size will have a much higher energy. So did you take that into account when you define what is an impact crater? That a smaller comet can make the same crater as a bigger asteroid?
Yeah, that's true. That is, you have there a factor velocity of impact, that is energy of impact, that is the impact velocity will be higher on average for Comet. But then you have things like, just to compare, that asteroids are more dense and comets might be for the same size, have less mass because the density of comets is much lower. And then you have some trade-off there between impact velocity and mass that you have really in a certain size.
I thought there was a question back here. Was there? Oh, okay. Bryce.
Hello, this is Bryce Bolin from Eureka Scientific. So my question is, I think this is very interesting. You talk about this long-lived structure, this long-lived, say, signature for objects with Qs in the outer planetary region. What I am wondering is if this you have a sufficiently recent stellar passage, can you backwards integrate the comets which come from, say, a single encounter interloper event and see which star they encountered, which caused them to enter the planetary region? Could that be a signature of a cometary shower? If they say you find a bunch of comets which have a common interloper perturber.
You look for the perturber. That is the problem. There was just a talk about a star that is going to pass very close to the sun in the future. But as far as I know, there are not any study indicating that a star that we have in the neighborhood passed close to the sun in the recent past. I don't know, I haven't seen any word about that. Because it's very difficult just to calculate the trajectory of the stars in the solar neighborhood.
Question over here?
Daniel for Fairprice Observatory in Stiller. Well, again, I got, with the stellar passages, you mentioned one passage every 13 million years. Is it irrespective of the mass of the star, or do we have more for substellar masses, brown dwarf, this kind of
That
things?
is, you know, this calculation is based on the number density of stars that we have in the solar neighborhood. These 7 stars that was indicated there per cubic parsec has a mixture of all types of stars.
Mm-hmm.
And therefore, the ones that predominate are these of smaller mass. That is, usually in the calculations, you use an average mass that is about a half of the solar mass.
Yeah, this is a follow-up question. So we heard yesterday that in 2 million years there is one star, Gliese, something coming at 10,000 AU. So you show that at 9,000 AU the shower is negligible, comparable to the background, but Gliese has a specific mass. So I was wondering if this applies to this star coming next.
This applies more or less has more or less the average mass. It's about 0.6.
0.6. So the numbers
solar
you
mass.
give
Yes, it's more or
apply
less
to that.
it's very standard star. Yes.
Nothing different.
Yeah.
Any other questions? I had one just to ask of, or at least maybe a summary of what I keep seeing is this discussion of basically comets that are coming to perihelion beyond Jupiter, so Saturn and beyond seem interesting. But we don't have many of them, and to me it doesn't feel like this is an observational effect that we're lacking in seeing them because we aren't looking at those distances, because Panstars can see it, there was dark energy survey, that I imagine at this point people would have found some of these, so why are we not seeing many of those objects? It seemed to be very, again, important for things like this and earlier talks. Why aren't we seeing any objects there? Is it just because they should jump to Jupiter and first, and so we often don't get that many out there? Or why haven't we really found many out there?
I think there is a very strong observational bias, because comets are very small, actually. And then you observe them, you observe a lot of them because they come close to the sun. When they come close to less than 2-3 astronomical units, then they become very active. They have displayed very huge coma, and then they can be easily observable by observers, even amateur astronomers. But when you are 10 AU, the activity is very low, and then you need you really need very large telescopes, large sky surveys in order to find some of them.
Yeah.
It's very tricky. Yeah.
But we do have centaurs that are in that region, so.
But the centaurs are very huge.
They are bigger.
Are bigger, yes.
Some kilometer objects.
Yeah, these are very big objects.
So maybe not appreciated. That's really an area where LSST will help, given the collection area. Cool. Any other questions? Colin.
Colin Snodgrass, University of Edinburgh. Do you have a feeling for sort of how many detections you need to start seeing, to convincingly start seeing clustering that you could say, oh, this is to do with a shower versus, just random background?
Well, I guess you need to have, because you have to have stars to cover all the sky. Then you have to proceed to see how many stars fall in every small area, and to see that is there are places where the number of stars is significant, is quite significantly above the average. And I guess that you need several hundreds of stars. That is, several decades ago, Biermann and Lewis in Germany, they tried to map the aphelion points of the long period comet population observed at the time. They claim to observe some clustering, but really it's difficult to notice there any clustering because the sample was not large enough. But I guess with the LSST, we just observe this. We can increase the sample in several hundreds of thousands of comets.
All right. Well, let's thank Julio and all of our speakers, because this ends the morning session.
Before I start, one thing, Hal, are you still there?
Yes.
Nice to hear from you. So if I could just tag on to that conversation, which I appreciate. Thank you for just letting me come in on Zoom so I can hear. I think, Hal, one response to your question, although you might not buy it, and I'm not leaning either way. One thing is that people think possibly is that the disk itself is optically thick to some extent, so the solar photons, especially if the sun was somewhat fainter, won't reach or much fewer of them will reach the comets at 10 or 20 AU when they're forming the disk in the first place. So there's some
true early on, but the gas is not going to last until the instability. Right? As Morby pointed out, we looked at this. If you have any gas around at all, you're not going to be able to get things into the Oort cloud. So there has to be a period of time where that isn't true. So
that's a good. I'm not saying that's the answer. I'm just saying that's one thing that people might say.
Fair enough.
Okay, so go ahead and get started. I guess you can see me and see my screen.
Yes.
Great. Well, I can't see I could see the podium, but I cannot see the audience. But thank you for letting me attend and give this talk virtually. So first of all, I wanted to say that I am presenting on behalf of David Jewett, who wishes he could be here and was supposed to be here and just recently had, without disclosing anything, just had an emergency that he cannot be able to be there in person. But he was also planning on being there in person with you, and I know that he regrets not being able to be with all of you. And I also, I'm filling in. I wish I could be with you also, but I wasn't able to travel there. So I very much appreciate Veronica for setting this up so that I could do this virtually. And in the spirit of what I believe Dave would like, I'm going to try as best as I can to give this talk the way that Dave would, I think, give it. I think I know many people there in the audience, and you probably know that on this topic of interstellar comets, I do have some of my own theories or beliefs. So I'm going to try, because it's a review talk, I will try as best as I can to be totally unbiased and not try to inject any of my own biases onto the information that I present here. But that being said, if you do have questions, so I'm going to stay away from things like theoretical potential hypotheses regarding Oumuamua. But if you do have questions about that, I'm happy to answer questions during the Q&A. And yes, I'm Darryl Seligman. I am currently an NSF, National Science Foundation, Astronomy and Astrophysics postdoc fellow and Simone NSF scholar. And I am also starting as an assistant professor in August in the Department of Physics and Astronomy at Michigan State University.
Congratulations.
Thank you, Hal. That was you, Hal, right?
Yep.
Yes, I'm no longer in Boulder, but it was nice to see you last year in person. So in this talk, I will first tell you what I'm going to do is first give you an overview of Oumuamua, which was the first interstellar object that we've discovered. And I'm going to empirically go through the mysterious properties that it exhibited. Then I'll tell you about the second interstellar comet. And this was an interstellar comet, not just interstellar object, Borisov, and present some of the extant observations that we've obtained of that object. And I'll end by telling you about future prospects with the Vera-Rubin Observatory and other all-sky surveys. And this is quite an exciting time right now because the Vera-Rubin Observatory, as many of you in the room know, I think Meg Schwam is actually there probably with you, or at least giving a talk soon. We have, she's running the LSST Solar System Science Collaboration and the operations. The first light is going to be happening in the next couple of months. So it's a very exciting time for this field. So the first interstellar object, Oumuamua, displayed many mysterious properties. So I have enumerated them into 8 different strange properties. So I'm going to now give you a kind of overview of, you've probably heard of many of these properties from me and other people, but I'm going to give you an overview of what the empirical observations were that led to all of these mysterious properties that we've inferred about Oumuamua. So the story starts back in 2017. This is the Minor Planet Electronic Circular that announced the discovery. I don't think I need to explain to anyone here in this audience what these electronic circulars are, but you could see in the fine print. Can you see my cursor if I use that?
No.
Okay, well, I can do it without that. That's fine. So in blue highlighted here, we have an eccentricity of 1.2. This object may be the first clear case of an interstellar comet. So that eccentricity of 1.2 shows us that this is clearly a hyperbolic trajectory. Now, this is Karen Meach had this very nice paper in Nature back in 2017, right after the discovery was announced. This is a collection of several data sets on the object. And they had a nice illustration of the trajectory, which I'm showing here. You can see in the bottom, you have the zoomed out version of Oumuamua's trajectory in black. And you can then see at the top right in the inset is a zoomed in view of Oumuamua passing through the inner solar system. So you can see here at that point, that black point labeled 1I 2017 U1, that's Oumuamua when it was discovered. So it was discovered at about 40 lunar distances from the Earth, as post-perihelion when it was leaving the solar system. And you can see that eccentricity, that's what the hyperbolic trajectory looks like. That is effectively why we know that Oumuamua must have formed elsewhere and is not from our solar system, because it had a hyperbolic trajectory and it came and left and is never coming back. So we can quantify this somewhat by comparing the eccentricity of Oumuamua, and I've also put Borisov here, so our unbound interstellar objects, with all of the comets that we know of in the solar system. So on the x-axis, this is the eccentricity. The y-axis is just a log scale histogram. And the blue and the pink bars are the short and long period comets. I was going to say respectively, but I think I mixed it up. So the pink ones are the short period comets. The blue ones are the long period comets. And the gray dashed line, that's where you have an eccentricity of 1. So that's where you're nominally below that have a bound orbit. So we can see that the short period comets are all bound to the solar system. And then the long period comets, we had a conference here. I guess I'm not there with you, but you are all at a conference in Stockholm about the Oort cloud. So people in the audience are probably somewhat familiar with the fact that these long period comets from the Oort cloud, there's an observational bias where you're more likely to see the objects with higher eccentricity. So you have a clustering of nearly unbound objects with very, very high eccentricity right at an eccentricity of 1, with a scattering of error bars. However, Oumuamua and Borisov, you can see on the right here, are safely hyperbolic objects. So that was its first mysterious property, that it had a hyperbolic trajectory. It was a pretty exciting time. I think a lot of people here in the audience will remember that, but if you're newer to the field and you weren't around in 2017, it was immediately a global media phenomenon. So these are just a few news articles following the days and weeks after Oumuamua was discovered. And it was so exciting because for the first time ever, we had the chance to look up close at an object that presumably formed in an exoplanetary or stellar system. It was also exciting, not just because of the scientific prospects, but the object was moving very rapidly. So we were only able to observe Oumuamua really from ground-based observatories anyway, for a couple of weeks with to get high-quality data. So this is just showing you everywhere in the world that we got photons on the ground from Oumuamua. And here I'm going to list the paper. This is every paper that reported either photometric or spectroscopic observations of Oumuamua. And I think some of these people are here in the audience as well, but there were nice papers published from Karen Meach, Dave Jewett. Those were the first couple. Joe Massiere actually got the first spectrum, Alan Fitzsimmons, and all the rest of these people here. So what these early observations showed was that even in deep stacks of images, Oumuamua displayed no cometary tail whatsoever. So the first deep stacks of images that were combined with many images were from Karen Meach's Nature paper and Dave Jewett's AppJ letter in 2018. This one that I'm showing here is the deep image that Dave put together using the Nordic Optical Telescope. And you can see that Oumuamua in the center here has no fuzzy qualities, clearly has no dust tail. So, and in fact, you can turn this into a limit on the amount of dust per second was being produced. So that's its second mysterious property, that there was no dust coma whatsoever. Now, Oumuamua, this is also slightly mysterious. I think it kind of depends on who you ask, how mysterious it is for what your expectation was. But Oumuamua had a slightly reddened color. So this is somewhat involved figure, so I will walk you through it. The x-axis is effectively just the color. It's the color normalized to the sun. The point is, in each of these small panels, histograms to the right are redder colors and histograms to the left are bluer colors. So in each panel, I'm showing the histograms of the colors that have been measured for different populations of solar system objects. So on the top, and that y-axis is just the number. So the top, you have the hot classicals, the scattered disks, the detached disks, and the cold classicals. The bottom, you have long period comets, short period comets, centaurs, and asteroids. And I just want you to focus on the black dashed line, that is Oumuamua. And what we can see, so it is slightly reddened. And most importantly, Oumuamua the color looks in line with what we see in all of the bodies in the solar systems, typically in a hand-wavy, unquantified way, except for the cold classicals. So the cold classical Kuiper Belt objects have an excess of this ultra-red material, remember the x-axis here, as you go to the right, is just redder material. And Oumuamua does not look like a cold classical Kuiper Belt object, at least in its surface reflection spectrum. And I would argue that is somewhat mysterious because the cold classicals have presumably been that some people argue that they formed in situ. There's that region of the cold classical Kuiper Belt is somewhat dynamically stable. So they've probably been there for a long time. So that you could argue there is also high energy radiation and cosmic rays very similar to the environment that Oumuamua is traveling through in the galaxy. So you could argue that those objects should be the most representative of what an interstellar object should look like. So the fact that Oumuamua did not look like a cold classical maybe is somewhat mysterious. So that's that third mysterious property, that there was no ultra-red material. But we could probably, although I don't encourage us to do that, we could probably sit here and argue about what you would expect the surface of Oumuamua to look like anyway for hours. Now, this, I think, is the strangest thing about Oumuamua. And this is a slightly subtle point. It's that Oumuamua was moving very slowly in the galaxy and implying that it has a very young age. Of course, it was moving very fast when we observed it, but that's purely because it was interstellar and had a hyperbolic trajectory. So most of the speed at which we observed its moving was actually just the motion of the sun as we, in the solar system, intercepted Oumuamua as it was sitting almost at rest with respect to the rest of the galaxy. And the reason the kinematics of an interstellar object are somewhat critical is that for tracer particles in the galaxy, dynamical processes such as scattering off of giant molecular clouds and substructure will eventually lead to dynamical heating or just increased velocity overall. So very roughly, at a kind of statistical level, you could say that there is a relationship between the typical dispersion or velocity, which I'm showing on the y-axis here, and the age of populations of objects in the galaxy, which I'm showing on the x-axis. So the blue line is the nominal fit from dispersion and age. And then on the left axis, right by the left y-axis, we have these different colored dashed lines. These are typical dispersions or velocities of different stellar populations. So all the way at the top, you have the oldest populations like white dwarfs. And all the way at the bottom, you have the youngest objects like giant molecular clouds. So giant molecular clouds typically move with dispersions of less than 10 kilometers per second because these are the most transient and youngest structures in the galaxy, while the oldest objects like white dwarfs are moving upwards of 100 kilometers per second. And the blue data here is just measured stars. So this is a somewhat empirical fit to the data. Now, Oumuamua was moving shockingly slow, almost at 10 kilometers per second. And that's shown here. I've outlined it in blue as well in the dashed line in pink. But Oumuamua's kinematics as it entered the solar system was only about 10 kilometers per second. And so that implies that it had a very young dynamical age, less than about 100 million years old. And that is younger than basically any stellar population. So that is very mysterious. Oumuamua also had very drastic brightness changes. So here we're showing the composite light curve. So this is a recreation of a very nice composite light curve that was in the Belton 2018 paper. And this is reporting all of the data that was taken, photometric data that was taken. And again, we have the list of all of the papers that published any observations of the object. You can see the y-axis is magnitude. The top panel here is when we really got the best data. It's only 6 days, 6 nights in October. There are some nights in November as well. It's also with Hubble Space Telescope. But you can see that Oumuamua displayed very drastic brightness changes by a factor of about 12 in linear scale, a factor of 12 in linear brightness variations. And we can compare that to what you see in light curve amplitudes of solar system objects. So in these histograms, I'm showing the light curve amplitude on the 2 panels. The top is in blue is everything bigger than a kilometer, and in the bottom one is everything smaller than a kilometer. Oumuamua was probably about 100 meters, so it's fairer to compare with the pink objects. But even with the smallest objects in the solar system, Oumuamua is an outlier in its amplitude. And Sergei Mashenko basically pointed out in 2019 by doing a fit to the light curve. I'm showing here, this is a fit that was done later by Astor Taylor, showing the best fit shape to the light curve. You can see what an observer would look at from Oumuamua as it's tracing the same nights here. You can see in red is Oumuamua's light curve and gray is the real data. That light curve is best fit by a 6 to 6 to 1 aspect ratio object. And that's a very extreme aspect ratio, more extreme than what we've seen in the solar system. So that's its 4th mysterious property, extreme shape. I know Hal also has some interesting ideas about what that shape could tell you about interstellar objects in general, if we want to talk to him later. The kind of weirdest property of Oumuamua was that it had a non-gravitational acceleration. So its trajectory could not be explained just by the gravity of the sun. Marco Michele and Davide Farnocchia identified this non-gravitational acceleration actually immediately and published it in Nature about 6 months after the discovery of the object, just because it took some time to publish, but they knew about the acceleration immediately in order to point follow-up data. And an interesting point here is that the magnitude of the acceleration was much stronger than those seen in comets. So again, I've got blue and pink as short and long period comets. Oumuamua, just focus on that here. The x-axis is non-gravitational acceleration magnitude. Oumuamua is all the way on the right and looks somewhat like an outlier. But an important point is that that is also a manifestation of the fact that Oumuamua is much smaller than these comets. So if we really what we want to compare is the non-gravitational force, which is the mass times the acceleration. So it's a much smaller subset of comets because these are comets where there are non-gravitational accelerations measured and radii measurements of the nucleus. But Oumuamua, when you look at mass times acceleration, is actually much lower in terms of force than those seen in comets. So it's certainly a precedented non-gravitational acceleration. The strange thing is that there was no apparent dust coma. And then to make it even stranger, you could argue, and I have argued, and other people have argued, that potentially Oumuamua was outgassing without producing dust, and that was causing the acceleration. But Dave Trilling also obtained Spitzer Space Telescope data of Oumuamua as it was leaving the solar system about a month after the discovery of the object when it was closest to the Earth, and got a significant non-detection of the object. So this is the result of the Spitzer data. This is where Oumuamua should be, and there's no detection. So that puts stringent limits on the production of CO and CO2. Here, there's a table in the annual review where we list every production rate that was constrained. Quanzi Yi had some nice constraints on carbon-based species. There was some radio observations that put not very constraining, but constraints nonetheless, production rates on OH, which is a daughter product of H2O. And then Dave Trilling's Spitzer Space Telescope data had limits on the CO and CO2. So that was maybe the 6th mysterious property, that it was not producing CO or CO2. And then finally, the detection of Oumuamua. Aaron Doe had a very nice paper quantifying this. the detection of one such object during the operations of pan-stars implies that there's on order about 10 to the 26 similar interstellar objects in the galaxy. So now we'll fast forward to 2019 when we discovered 2I Borisov, the next interstellar object. So this second interstellar object was discovered right before the COVID pandemic, actually, just a couple of months before. It was discovered by an amateur astronomer whose last name is Borisov, so named after him. Borisov was discovered in 2019, and this is the trajectory. So the eccentricity was much higher than that of Oumuamua. And most importantly, it also was discovered significantly prior to perihelion. So it was discovered with many months with which it would be observable with our telescopes. So there was upwards of a year of time, a year maybe not, it got cut, a lot of programs was cut short because of the COVID pandemic, but nominally with the trajectory, it was observable for upwards of a year with some facilities that we have. So we had ample opportunity to take detailed measurements of Borisov, unlike Oumuamua. And kind of in every way that Oumuamua was mysterious and defied our expectations, Borisov looked a lot more like a solar system comet. But there are some differences between Borisov and solar system comets. So I don't want you to think that Borisov was somewhat non-interesting, because there are differences between Borisov and the solar system comets. It just was a stark contrast to Oumuamua. And I think this, I know Dave really loves this image that we put in the side-by-side comparison that's in the abstract, and this is also in the annual review. On the left, you see the Nordic Optical Telescope image of Oumuamua, and on the right, these are Hubble Space Telescope images of 2I Borisov. And you can clearly see that there is a distinct dust coma around Borisov. So Borisov was actively producing outgassing volatiles and producing dust for the entirety of the trajectory that we were able, the entirety of the visible apparition. And that's excellent because there were several months with which we were able to get, and the collective we, it was not actually me, this was not any of my work, but this were people, some of whom were probably in the audience and all across the world, were able to get detailed measurements, not only of the dust production, but of spectroscopic measurements to get various production rates of different volatile species. So we had enough time to measure rates of production of different volatile species in Borisov and compare them throughout the apparition. So this is showing you all I did was just grabbed everyone else's measurements. So you put every measurement that was published of Borisov together. The x-axis here is time relative to perihelion. So at time of 0, and it's in days, that's probably worth noting. So at time of 0, that's when Borisov was closest to the sun. The negative time to the left is the first couple of months as it was inbound, when you got a lot of observations, specifically ground-based observations. And then on the right is as it was going outbound, so for a couple of months while it was observable. And you might note that the kind of ground-based observations kind of fall off. That's because COVID pandemic happened, unfortunately. Another thing that's worth noting, actually, I wanted to, can you see my full screen? Because I have the Zoom boxes blocking the top legend. You can see it says CO and CO2 and H2O, presumably. Okay, so the production rates do have a log scale, and the bottom panel, there's a break in the axis. So the bottom ones are showing you, this is everything that was measured. So you have carbon-based species, CN, C2, C3, NH2, and HCN. It was producing at a much higher rate by a couple of orders of magnitude, so it would have looked a little silly to not break the axes. But there are measurements of H2O and CO. And something that is interesting is that Borisov, when there were contemporaneous observations of CO and H2O, Borisov was producing more CO than H2O, which you could see at the right around perihelion and to the right of perihelion. So these two tables, I'm showing you both of these tables here. I'm going to flash between them, but this is every paper that put together a production rate from Borisov. So some of these people, I believe, are potentially in the audience, but these were all of those measurements. And of particular worth noting is Here we have the measurements of CO in Borisov from these Yang, and then Dennis Bodowitz and Martin Cordner had these two papers, both published kind of contemporaneously in Nature Astronomy. And what they argued was that because Borisov was enriched in CO, remember CO is, some people refer to as a hypervolatile. Effectively, it is harder for a comet to retain CO than water. So as Borisov traveled through the galaxy, presumably you're losing CO at a higher rate than water. So the fact that there was more CO than water after all of that processing implies that Borisov must have formed, these two papers basically argued, either in the most distant regions of a protoplanetary disk, or potentially in an M dwarf star system with a very low temperature, so that the CO snow line was very close in, or some combination of those in a colder star system and at a further region. But it looks somewhat different than the solar system comets because of this enrichment in hypervolatiles, which also gets back to Hal's question for the last talk. And so now I'll end in just the last couple of minutes I have remaining by telling you about why you should be excited about this field. Although we haven't discovered an interstellar object since 2019, we should be discovering many more of them very soon. So we have the Vera Rubin Observatory, which is still slated to be coming online very soon. This is a somewhat outdated now video, but this was after the construction was finished of a fly around of the dome, and the Rubin Observatory in the Atacama Desert is about to go online this summer and collecting photons. The camera was just installed, and this should give us near nightly coverage of the entire southern hemisphere, and up to upwards of 5 orders of magnitude more sensitive than our current all-sky surveys, such as ATLAS and Pan-STARRS. So we should be discovering many more of interstellar objects like Oumuamua and Borisov in the coming months. This is just showing you some highlights of LSST website is showing highlights of potentially discovering interstellar objects. I'll note here that Dusan Marcheta in Serbia there has been a lot of efforts to simulate the population of interstellar objects that we should be discovering. Dusan Marcheta put together a very nice paper that was able to do very computationally efficient simulations of various populations of interstellar objects with different albedos and size frequency distributions and different stellar kinematics, M dwarfs, G dwarfs, and OB stars, just as examples. This was only feasible, this huge computational effort was only feasible because Dusan had implemented had developed and implemented a methodology to produce the population that was purely analytic, so provided about 7 orders of magnitude increase in computational efficiency than anyone else had done beforehand. So he's able to then produce thousands of different populations of interstellar objects. And the takeaway was he then ran it through the LSST survey simulator and found that these plots are showing you as a function, if you just focus on one subplot for one type of kinematic, the x-axis being the albedo of the population, the y-axis being the slope of the size frequency distribution, anywhere between kind of the ranges we see in the solar system, and the color is the number of objects discovered or discoverable by LSST, anywhere between 0 and 50 per year. So the point is not to say how many LSST will find, but more so what the distributions should look like. And then once LSST starts finding them, we can then constrain things using models like this about the size frequency distribution, albedos, and kinematics of the populations. We also have there are probably members of the European Space Agency mission Comet Interceptor in the audience. This is a very exciting mission that will be flying in 2029. And if there is a suitable, it's slated to visit a long period comet, but if there is a suitable interstellar object target, the Comet Interceptor will rendezvous with an interstellar object. So we might even have a space mission to an interstellar object. I think Meg Schwamm is giving a talk later in this conference. I don't think she already gave her talk, but she gave it yesterday. Okay, so I was wrong. Oh, Meg's right there. Hi, Meg. So Meg runs the LSST Solar System Science Collaboration, and I'm sure she gave a wonderful talk yesterday, and probably already talked about the Solar System Science Collaboration, but this is a very exciting time for the collaboration because LSST is coming online soon. So please talk to Meg or me. I'm on the Rubin Users Committee if you're interested in getting more involved. And I will leave my slides here with some conclusions and take any questions. Thank you very much.
Maybe it's nice for Darryl to stand over there if you ask the questions, we can see you.
We can see the audio
Oh,
Yeah, you can see the audio. Okay, then maybe just speak up.
Hal Levison from Southwest Research Institute in Boulder. Hi, Darryl, nice talk. I'm curious about the overall population of interstellar comets. You gave a number, right? I forget what the number was.
10 to the 26.
10 to 26.
Okay, so we got into a discussion earlier today of what fraction of stars actually form Oort clouds.
Oh, interesting.
Okay, and this is an important constraint for that, I think. Right?
Yes.
So there's about 10 to the 11th stars, right, in the galaxy, the 0th order. So, you know, it looks like, right, we're getting about 10 to the 15th interstellar comets for every star in the galaxy, right, which is about 1,000 times bigger than the number of comets in the Oort cloud. Right, which is sort of consistent with the idea that all stars form Oort clouds. And I was wondering what your thinking is about that.
Yeah, Hal, thank you for pointing that out because I certainly did through this point. So that 10 to the 26 number, remember, okay, so it is very hand-wavy. And I don't think anyone would argue that, you know, you're effectively using just a population of 1 to constrain that number. Because Borisov, because it was not discovered on a well-characterized surface, doesn't give you any constraint. And there's probably orders of magnitudes of uncertainty on the number, but you're correct that 10 to the 26-ish is about an Earth mass per star in the galaxy, based on the size of a Oumuamua. So I believe it is telling you, that's kind of what I was excited about Oumuamua in the first place when it was discovered, even though I wasn't actually working on small bodies whatsoever. It implies that you are producing, typically on average, every star is producing a large amount of interstellar objects and Oort clouds, because presumably they form in a very similar manner. So I think that is exciting. And I think it's worth noting there are several other independent lines of evidence to believe that that's true. First of all, there was a nice Nature Astronomy paper a couple years ago about an excess in, I think it was Upper Scotius, if I'm pronouncing that correctly, the nearby star forming region that was only a couple million years old. They had an excess of detections of free-floating Jupiter mass objects and implied that within the first 10 million years of formation, planetary systems were on average ejecting upwards of 10 Earth masses per star. Basically from free-floating objects, you have an entirely independent constraint which lines up with the number predicted from Oumuamua. And also, there's another line of evidence, which is that if you look at what surveys using ALMA, mostly ALMA, have shown from protoplanetary disks, you'll see that in non-protoplanetary disks, you'll see it is somewhat ubiquitous that you get substructure such as rings, spirals, and gaps. And if you were to, you don't have to believe it, but if you were to believe that the gaps in those substructures were caused by giant planets, then it effectively implies every other star has a Neptune analog. And Neptune should be good at ejecting interstellar objects. So that would also imply that if Neptunes were creating exoplanetary Neptunes were somewhat ubiquitous in forming Oort clouds. Does that answer your question?
Oh, yes. Thank you.
Okay, I think we have to wrap it up because we have to move on. let's thank Darryl again.
Thank you.
Next will be Pedro Lacerda talking about light curves in comets.
I want to first thank. Yeah, I'm very grateful for being here. I think this is a really good idea. I've told this to different people. This type of meeting, this size of meeting. This is not my talk. This type of meeting, very focused on one subject that I think is underrepresented in the meetings we generally go to, is very good. The size is great. The times for coffee, for meals are big. It's good for discussion. So I really appreciate it. I'm really happy. I've learned a lot. Most of my activity in astronomy has been dealing with Kuiper belt objects and centaurs. I always stayed away from comets because they're too messy. But in the last 2 years, I've been working on comets. So I'm quite fresh in this field, and I've learned a lot just in this meeting. So it's very good. And I also want to thank Veronica and the staff, just like Thomas Quinn did, because you're doing a great job. It's very well organized. Okay. That's the first slide. The talk is based on the paper that came out in March or April, which was motivated. So I'll start with the motivation and introduction. It was motivated by Comet Interceptor mission preparation. I'm with Colin. I'm part of the science working group where we're thinking about trying to figure out what to expect from a target that we don't know what it's going to be like. And these questions came about. Can we predict the 1 AU brightness of a long period comet when it's discovered at 10 AU? So let's see if I can point. So based on the magnitude at discovery, can we predict what the magnitude will be at 1 AU? And someone also mentioned in the discussion, is it true that dynamically new comets brighten more slowly as they come in? And do we have statistics for that? So it was based on these two questions that I started looking into this problem. And so the conversation will be focusing on this type of data. So this is distance from the sun and magnitudes. If you're looking from Earth, you can fit sort of these curves with a total magnitude being some sort of absolute magnitude, plus a dependence on geocentric distance and then a dependence on heliocentric distance. But if you subtract the geocentric contribution and you turn this into essentially a heliocentric magnitude, which just has these two parameters, m, which is the magnitude at 1 AU from the sun, and k, which is the slope of the brightening. This k, I used k, but in a lot of literature, this is written as n. And this is the relation between k and n. And n is the so-called activity index, and n is more physical. It's basically the slope of the power law with heliocentric distance as the comet is coming in. But I use k, just k log r. The first paper that I found looking at this sort of systematically is actually by Oort. It's this paper, 1951. The title is Differences Between New and Old Comets. And this is a cutout of a table in that paper. And this is a sentence, I think, from the abstract. New comets are characterized by the slowness with which their brightness varies with distance from the sun. And indeed, dynamically new comets here have a shallower slope coming in than dynamically old comets. And the ones in between are in between. Later, Whipple also writes in a paper in 1978, I think also in the abstract, added a bit more data, but basically says the same thing. New comets approach perihelion with smaller values of n, and older comets with increasingly larger values. In the meantime, and then other people have looked at this, but this is a difficult work to do because it always suffers from problems which are small numbers. In the past, especially before surveys, these were biased samples because we only knew about low perihelion comets. We only got observations close to the sun. So I thought we must have now lots of historical data, and we should be able to do this better. We've seen this plot a lot in the conference, so this is the dynamical classification I'm using. I'm just following the Oort's classification into new. Oort called the intermediate ones fairly new and then old, but I call them intermediate. And this is the energy. This is 1 over A0, and these are the cuts between new, things beyond 10, come up from beyond 10,000 AU, intermediate, and old are inside 500 AU. And inside this 25 AU are what Oort called the periodic comets, short period. We're not going to talk about those at all. And these are here's the distances in the orbital periods of these comets. Okay, the data. The largest set of, so my approach, we've seen talks that mentioned, more careful data. There's papers that look at better quality data, but the numbers are small. I went for, as many data as I can get. So try to hope that in large numbers you're protected and you can do statistics and you can sort of find trends. That was the approach. So the data source that I used is really nasty data, but there's a lot of it. So it's the cometary magnitudes reported to the Minor Planet Center. The bad thing is that this is very, very heterogeneous data because it's taken from different observers. All of them use different processing techniques. So on the right, you see just a sample. Each box is a comet. Horizontal is distance from the sun, and vertical is magnitudes. And you see some of these curves have lots of, and the different colors are different observers. So this is just a sample to show that these things show lots of scatter. But the advantage is lots of it. About over a million measurements taken at almost 1,000 observatories, covering 0.3 to 35 AU in distance from the sun. 99% of the data, this is a good thing, is post-1996 because of surveys that came in since then. And that's a good thing, because surveys are a little bit more behaved. Okay, so to clean this mess, I went through 2 steps. One is looking at the dynamics. What can I say about the dynamics of the comets? And the other one is the magnitudes. So the dynamics, these were the steps I followed. So I started with each C comet in the JPL solar system database. And then I went through this process of, is the original orbit, do we have a reliable original orbit for this comet? And the MPC provides these numbers. I also looked at papers by Krolikovsky et al., the Nakano notes, and generally found consistency between these things. But still, I took the most stringent uncertainty on the 1 over A0, and I made sure that the number that is measured is at least 3 sigma of the uncertainty to get rid of unbound orbits. So it's just to make sure these are 3 sigma bound. Then comets that survive this dynamical stuff, I just look, do they have MPC magnitudes? And for the ones that do, I queried JPL Horizons to get R and delta for all these magnitudes. And the result is 250,000 measurements for about 740 comets. And each data point, I know exactly where the comet was, distance from the sun, so you can calculate that brightening curve. Then we have to deal with the magnitudes. So this is for one of these curves, for example, and different colors here indicate different filters that the observations are taken in. What I did was to try to compare apples to apples is I separated these observations into observations taken by a single observer. So these numbers on the top of these boxes are observatory codes, so they're taken from a certain observatory, F51, this is Pan-STARRS. And then inside the observations of each observatory, I also looked separately at each filter that they used. And this is what I call, so down here I have what I call the global curve. This combines all the data, and this is actually quite a clean example. There's messier examples. And these are called the global curve, captures the global brightening behavior. And these here, the separated by single observer, single filter sequences, I call them strands. And the strands capture local brightening rates. And so I fit this expression to this as a single one. You already see that it's not a very accurate fit, but it gives you a general slope. And then to each of these strands, the valid ones, because I require these strands to actually be good things to measure slope. They need to have a certain number of points. They need to have a certain range in heliocentric distance. They need not to be bimodal, otherwise the slope is totally decided by 2 clumps of data and things like that. But the ones that pass those tests are the ones that have here a little black line through them. You see that they're already much better fit by this expression because they're sort of local. And these give me local brightening rates. They're like measured of the local brightening rate of certain heliocentric distances. So finally I get about 1,000 of these strands that I considered valid and 346 of these global curves on a total of 272 comets. There's more global curves than comets because some comets have a global curve coming in and then a global curve going out. So I also looked at the post-perihelion behavior. This is an example, a more realistic example. Shows you here, now the distance is not in a log scale, so the line actually looks like a curve. But see, the original data is very messy. These are all the observatories that looked at it, and they're all here, so it's messy. But here are strands, and these are broken up by, as I said, observer and filter. And you see they're much nicer. They're like you're comparing things that have been done by the same person at the same observatory with the same technique. So they're well behaved. So this gives me the M1 and K1 parameters. The M1 is the global magnitude when it reaches 1 AU, and the K1 is the global brightening slope. And these KRs are like local slopes of the brightening curve. So you have heliocentric information. So this is an important point. Each comet has one M1, one K1, but each comet has multiple KRs, which gives you the slope as it comes in. All right, results. So the first result is this question of do dynamically new comets brighten differently from dynamically old comets? This is a cumulative distribution function. This is a cumulative fraction of comets. New comets are the blue line, yellow line is intermediate comets, and the red line is old comets. And this is the brightening slope, so this is the slope of the strands, let's say. And yes, newer comets brighten more slowly than old comets. The blue and even the yellow line are to the left of the red line. So if you prefer the numbers, so here's the medians and the average of these distributions and the interquartile ranges. So this shows, and the difference between the new and the old comets is significant at better than 3 sigma. So there is a difference. New comets brighten more slowly. Second plot has already been shown by reversed, the flipped version by Jessica, is that the brightening rate, so as the comets are coming in, and my plot, they come in from the right. That's why Jessica had to flip them. They're coming in from the right, and the vertical is the slope of the brightening. And new comets start out steeper, but their slope comes down and sort of flattens inside 3 AU. Intermediate comets have a sort of intermediate behavior, but it's more or less the same. And old comets, the slope doesn't really change with heliocentric distance. So the brightening rate of the newer comets, I'm calling newer the new and the intermediate, is distance dependent. It changes from a rate of around 12.5 magnitudes per log AU beyond 3 AU, and it drops to 7.5 inside that distance. Whereas old comets, they have a steeper brightening at all distances of about 15 magnitudes per log AU. Now, the intrinsic brightness of the comet, the best parameter in the data to assess that is this M1 parameter. And this is the M1 parameter cumulative distributions of new, intermediate, and old comets. And here again, we see that the new and intermediate comets are intrinsically brighter. Their distribution is to the left of the old comets. So that's the conclusion here. New comets are intrinsically brighter. They have smaller M1 values. And the difference is, again, significant. Yeah, so this is interesting. It's another interesting result. So it's starting to answer these questions with large numbers. Okay, looking at the fading. now the fading rates, they are actually similar across the dynamical groups. This is the cumulative distributions of now the fading rates past perihelion, the comets are fading. And these are, the most distinct are the old and the intermediate populations, but the p-val is 0.19, so this is not significant. They're not different. This graph on the right shows the slope pre-perihelion. So to the right, you have comets that come in with a sharper increase in brightness, versus the slope change post-perihelion. 0 means it didn't change. So above this horizontal line, the comet came in with a certain slope and left with a steeper slope. The fading slope is steeper. And comets below the dashed line come in with a certain slope and go away shallower. And in terms of numbers, approximately equal numbers within all the different dynamical families is the same, the behavior. Approximately equal number of comets display positive and negative change in this from brightening to fading slope. So it's kind of random. But there's this trend that, especially for these are the yellow again are intermediate and the blue are new comets, there's this trend that steeper brightening pre-perihelion, so comets to the right, leads to shallower fading. You know, they fade very much after perihelion. Which, if you assume that the fading slope when they go away, if they come back, that this fading slope is representative of what their brightening slope will be when they come in again, this leads to a sort of asymptotic behavior because this comet will be thrown to the left. And this thing actually circulates and makes the asymptotically, mathematically, this will tend to a slope of k of 10 if they repeat their returns. Okay, the question of can we predict the magnitudes at 1 AU? We can try. It's hard. There's a lot of uncertainty. This graph here, there's no fitting. This is really just looking at the magnitudes. So what I do here is I take the magnitudes of comets that actually reach 1 AU from the 272. There's not that many, but there's a decent number. And then I just do the difference of the magnitudes that they had at a certain distance minus what they eventually got at 1 AU. So what this plot says is if you discover a new comet, blue line, at 9 AU, between 9 AU and 1 AU, it will brighten by about 8 magnitudes, plus or minus this bit. And the intermediate comets have a kind of a similar behavior, but you see that the old comets brighten much more steeply, a different way of looking at it. So these curves can be turned into a table, and you can actually write the probability distribution for these curves. And so you can write the probability distribution of the 1 AU magnitude of a comet given the discovery at 9 AU. Yeah. Now a bit into more the speculative bits. Yes? Okay. Sizes. This is the size of the nucleus in a log scale versus this M1 parameter. So I looked, Dave Jewett published this nice data set of sizes. He measures this is all model dependent, but he models the size based on two things. One is the non-gravitational acceleration effects, and the other one is the total production rate of dust. Both are model dependent, but this set of points are the ones where the two numbers agree, and they're independent, so there's no reason for them to agree. And this question, we find that new comets are intrinsically brighter. These blue and yellow, so the blue dots are intrinsically brighter. They're up here on average. But the question is, are they more active or are they larger in nuclei? And what this plot kind of suggests, low number statistics, is that the larger nuclei also tend to be the brighter nuclei. And the new comets, there's a concentration of new comets here on the largest nuclei. So, in this small number statistics indicates that new comets are indeed larger. They have a larger median size. This is also something I already said. 4 of the largest 5 nuclei down here belong to new comets. And the same data suggests, if you look now just at the blue points and the yellow points, so the new and intermediate comets, there's a trend here that brighter nuclei are larger. And that's not the case for the old comets. The old comets they don't display really any trend based on these 4 points, admittedly. Also, the new comet brightness is consistent with being proportional. If you look at this, is the brightness in flux being proportional to the nucleus radius to the cube, and this is to the power of 2. And the power of 2 is the activity being proportional to the nucleus surface area, and this line is slightly better representation of the trend of the new and the intermediate comets. Okay, then I'm a bit short on time, but there's this intriguing relation that I found, and Oort had found this in his 1951 paper, between this M1 and K1 parameter. The relation, that's what I'm plotting here, M1 versus K1. So brightening rate versus intrinsic brightness. Blue line is the new comets, yellow is the intermediate, and red is the old comets. And the lines are fit to actually the point. So the point is what matters, and the lines are just fit. But the relation implies that brighter comets brighten faster. What's interesting is that new comets, the blue dots, are much more tightly clustered around the line. They're much better fit by this line. And this means that M1 plus K1 almost is constant. That's what this blue line means, which means that these comets all have the same magnitude at 10 AUU, roughly, which is really strange. But new comets have their distributions are also narrower in other properties that I've shown here. So this could be a bias, but if it's not, it sort of suggests that maybe new comets are more uniform in their behavior. They're kind of all the same, to first order, compared to old comets. This is highly speculative. Okay, conclusions, that's this slide, and I hope I still have some time. So these are all things I've said, but this is the whole talk in one plot. This is the brightening, comets coming in from 10 AU to 1 AU, old comets, intermediate comets, and new comets, and this is the fading slopes. And what these lines are, they're the median, these distributions that I've shown you, these are the medians of those distributions plotted as simple lines. So you see that new comets are brighter, so the line is up here, and then you have this, and then you have the old comets. They have the kink around 3 AU, where the slope of the line changes, whereas the old comets don't show that, and the brightening slopes are all the same. And yeah, this is my talk. Thank you very much.
Any questions?
So you were referencing the code database, I think, right?
For the 1/A0s.
Yes.
Yeah, I looked at that as well, yes. That's not the one. I ended up using the MPC numbers just because they cover all of my comets, and the code database doesn't. But the ones that I have numbers from both sides, they kind of agree.
Okay, yes, because the code database, I think, goes to the latest as 2017, but what's nice about it is that they examined the previous orbital history of the object, so you get like a pretty nice idea of what the dynamical classification of each comet is like.
Yeah, they do a more careful job than the MPC. What I looked at is, would my classification of new, intermediate, and old comets, especially new and old, change dramatically if I used one or the other, and it doesn't. So then it doesn't matter. There are shifts, but they're not very significant.
I'm a bit confused by your claim that the new comets are bigger, because you would expect from the Oort cloud to get a full-size distribution, including also smaller objects.
Yeah.
And you also say that basically the entire surface is active because it's proportional to the radius, to the luminosity is proportional to the radius to the square. So I would always thought that actually, and this is also why we see so many coming from the Oort cloud, that they are intrinsically brighter per unit surface, and so they are smaller. The bias is due to magnitude. So think about that.
Yeah. First of all, this that claim of that the brightness goes with R squared is based on this line and those points. So it's not. It could very well not be true. So we need much more data. The problem is it's very hard to get the sizes of the nuclei. Even all of these sizes are model dependent. But your other point, yeah, I agree. The nuclei should have a size distribution. They should not all be the same. That claim of, it's not a claim, it's just getting me to think about it. Are they all the same? Is the fact, is this blue line is the blue points clustering much more tightly around this blue line than, for example, the old comets, the red dots, they scatter all over the place. And if this M1 plus K1 is constant, that sort of implies that they're all equally bright at 10 AU. And how can you explain that? It could be that you're looking at the tip of the iceberg of what you can detect. So it's a detectability bias, but that would mean, you would be missing on, so this is brightness, intrinsic brightness. You just wouldn't see points. Let me put it this way. That doesn't work for the brightening rate. So you could still see comets that brighten more slowly. You could see blue points here. They just brighten more slowly, and they're very bright. We could see, and we don't. So, yeah.
I'm intrigued, of course, by this all newcomers being rather similar, while the old ones are not that similar. And does this correlate with the perihelion distance?
No, so I didn't find, previous work had found correlations with perihelion distance because they suffered much more from this selection bias that, you would only, it had to do basically with the selection bias. And this because there's way more comets and it uses survey data, is less implicated by that. And I didn't find any correlations with perihelion distance. What I do find, which affects some of the conclusions here, is that my whole sample of 272 comets, the median perihelion distance of the blue dots of the new comets is larger than the median perihelion distance of the old comets. Which means that I'm...
Say it again.
The blue dots, they have, their median perihelion is slightly further out, about 1 AU on the median, than the red dots. Which means that, I'm seeing, on average, the blue dots 1 AU further away than the red dots, which could explain, for example, why their intrinsic brightness looks bigger. It's just a selection bias.
Yes, Julio Fernández. I worked several years ago in the problem of magnitudes and how related to the fraction of active area. And the results were that the fraction of active area in Jupiter family comets was actually very, very small, even smaller than 1% in some comets. Therefore, they could be very large in size, but very little active, and that reflects in the total magnitude that is very fine. And that might have to do also with what you find the Jupiter family comets tend to brighten more than long period comets when they get close to perihelion. Simply because they have dust mantles. The dust mantles, of a fraction of the dust mantle tend to be purged, and then
that leads to a brightening.
And then the comet becomes more active.
Yeah. Okay.
All right, let's thank Pedro again. And we'll move on to the last talk of the conference by Bryce Bolin. Volatile comet and big giant.
Hello, everyone. Yes, it's the last talk. Hope it's a good one for you. Worth going through this entire conference. It's been a great conference so far. I'm going to talk about how the observed activity of Comet C2014U and 271 Bernadette-Bernstein tells us certain things about the formation of the Oort cloud, namely its formation time. So let's talk about this comet. This is a comet that was discovered, and it was officially announced in June of 2021.
but the earliest detections were found in 2014. So it has a designation as a comet discovery made in the year 2014. It has a perihelion distance of 11 AU, just around the orbit of Saturn, and a semi-major axis of around 20,000 AU. So I want to point out here, this is a nice plot made by Tim Lister, showing the discovery date of comets and their distance at which they are discovered from the sun at the time of their discovery. And so you can see before the year 2000, most comets were discovered at a distance around 4.5 AU. And this is approximately where we have the water ice sublimation line. And after the year 2000, we have more advanced technology, consumer-grade charge-coupled devices, enhanced the sensitivity of ground-based surveys, resulting in comet discoveries going out to 13 AU, and this is approximately where the CO2 ice line is. And beyond that, in the late 2010s, we start to discover comets that are well beyond the CO2 sublimation line. The most extreme of which found so far is C2014 UN271, which was discovered at around 30 astronomical units. So this is a image, some images taken with the Hubble Space Telescope of comet C2014 UN271 when it was 19.5 AU from the sun. The colors are about neutral, about solar colors, solar color. And even at 19.5 AU, we start to see a tail. So in the left-hand panel here, we have a synchrone diagram of the comet where I've never used one of these things before. I'm going to try to do the laser pointer thing. Okay, it's kind of like a Wii, if anyone played with Nintendo Wii. So you can see here that there is a anti-solar tail. The sun direction is in this direction right here, but the tail goes in the approximately the anti-solar direction. So even at 19.5 AU, we do have the effect of solar radiation pressure on the trajectory of the dust particles that are being emitted from the comet's surface. The most important thing about this comet's activity is, however, that it was observed to become active starting at around 26 AU. We have detections of the comet going out far as 30 AU, but beyond 26 AU, the comet has a relatively, let's say, inert appearance, where starting at around inside 26 AU, we start to see the formation of a tail in the anti-solar direction. So this is what we call the delayed onset of activity, whereas the comet is coming in from the Oort cloud into the planetary region. It becomes active at a distance inside of the CO sublimation line at 120 AU. So I'm going to talk a little bit about the orbit. So this comet is from the Oort spike. It has a 1/A of around 10 to the -4. Its location where it comes from inside the Oort cloud is what we would call the outer Oort cloud. I've plotted here its semi-major axis inclination with respect to the solar system and the galaxy, as well as the eccentricity. And it appears to have the dynamical properties of a new comet from the outer Oort cloud. So I'm going to talk a little bit about the formation of the Oort cloud. We've discussed this many times, but the idea is that as it pertains to Bernstein, it's important to emphasize the fact that the comets all came from, we'll say the majority of them came from the Trans-Neptunian disk, which started at around 24 AU. The most successful outcomes of the NEAS model have a planetesimal disk of around 20 Earth masses starting at around 25 AU, and 6% of it is ejected into the Oort cloud. And we have a upper bound on the formation of the Oort cloud as from the giant planet instability of less than 100 million years, provided by evidence from the Jovian-Trojan binaries. This was investigated by Nesforny 2018, that if you have a timing of the instability that occurs after this, the collisional grinding inside the transit-Tunian disk is too severe for the Jovian-Trojan binary to survive. However, the lower bound on this is not so well constrained. We have upper bound for the timing of the formation of the Oort cloud, but we do not have a lower bound. One other interesting property of the fact that this comes from the outer Oort cloud, or from the Oort cloud at all, is that this object had a previous perihelion of 250 AU. So this is from the makers of the code database. I think they do amazing work. But this is showing the orbital evolution of C2014 UN271 from -3 million years to +5 million years. And we can see that starting at around today and going back in about 2.5 million years ago, the comet had a previous perihelion distance of 250 AU. It encountered the star HD 7977, which kicked the perihelion going from a 250 AU perihelion to something that's more about what it is today, around between 10 and 20 AU, to where finally today has a perihelion distance of 11 AU. So what this means is that the comet was basically outside the CO2, H2O, and CO sublimation lines while it was in the Oort cloud. So this here is a plot that shows the production rate as a function of temperature for H2O, CO2, and CO from Liss et al. 2020. And we can see that the production rate drops precipitously for CO2 for distances. It's basically null. This is a logarithmic scale here for distances past 5 AU, and then drops precipitously for CO past 15 AU and CO2, and then for CO it drops out precipitously past 200 AU. Basically, the production is more or less null, where UN271 had its perihelion distance previously to its now inward journey into the planetary region of the solar system. So another interesting thing about this is that the comet is pretty large. We knew that from the discovery circumstances that the comet could be large, but we did not know exactly what the contribution to the light scattering cross-section was from its dust and from its nucleus until Lelouch et al. Observed it in 233 gigahertz frequency wavelengths using ALMA, which the radiometric observations reveal the emission from the comet, basically eschewing all dust at the superior resolution enabled by these observations, around 0.06 arc seconds, and at a wavelength at which you would not see most small micron-sized dust. So when this observation here, we're seeing the emission is entirely from the nucleus itself, which implies, based on its intensity, that it has a diameter of 140 kilometers, using the near-Earth asteroid thermal model. Also, Hui et al. Observed the comet with Hubble, and they were able to place a constraint on the comet's albedo, combining the Lelouch et al. Diameter with their visible light observations from Hubble to show that it has an albedo of about 5%. So using the size in mind, it's actually very important to consider exactly what we are talking about here in terms of intactness. So this is from Botke et al. 2023, work done in collaboration with Raphael Marchel, who shows that you have more or less a survival rate as a function of diameter. You have on the y-axis over here, you have the cumulative size distribution, and then you have the ratio between the initial size distribution and the present day size distribution, where the initial size distribution of the transit-Tunian disk is given by this purple line. The current day size distribution is given by this, I guess that's cyan, and then the ratio between the two is this yellow line. So that we see that for all objects that are approximately about 80-ish kilometers or larger, the ratio is more or less 1. But below that, especially once you get to below tens of kilometers, let's say, ratio drops below 10%, and it's basically everything's a collisional fragment below that. All of these things taken into account suggests that this is a collisionally intact planetesimal. And just for context here, this is a rogues gallery of all the other comets which are of notable size. We have Hale-Bopp right here, 75 kilometers in diameter. And then there's a couple of other objects from the scattered disk of say, tens of kilometers in size. But UN-271 is by far the largest of these examples, and with the noted fact that it comes directly from the Oort cloud. So here are some characteristics briefly summarizing why this object is, some of the notable properties of this object. So more or less, it is basically, let's say, the best, most pristine example of a dynamically new comet from our solar system. So when this was discovered, its discovery was announced in June of 2021, I immediately applied for time on Hubble through the director's discretionary time. A day later, I received a note saying, "Oh, just do the mid-cycle," and I applied for time in mid-cycle, and I got the data, and that's what I showed earlier. But as soon as the director's discretionary opportunity became available for Hubble, sometime in the fall of 2022, I applied for DD time to observe it with IFU mode near spec. And it was the very first DD project awarded out of all of astrophysics. That includes things like supernova, cosmology, et cetera, et cetera. The first DD award for JWST was a comet. So go us, I guess. And just for a little bit, I'm saying this for comedy here, is that I was also awarded the very last DD for Spitzer before they turned it off in January of 2022. January of 2020. So I effectively bookend the near-infrared spaceborne observatories from the perspective of director's discretionary time. And I'm planning on doing the same thing with the next generation near-infrared spaceborne survey. But anyhow, so we so far have taken 4 observations in near-spec IFU of the comet starting December 22nd of 2022 through October 9th of 2024. Covering heliocentric distances between 18.2 AU to 15.9 AU. So this is the first view of the comet from December of 2022 with the near-spec IFU. These are at 4 separate key wavelengths. We have 1.7 microns here, which is just a continuum. But then I show H2O ice absorption feature, or let's say the 3 micron feature, which is not just H2O ice, it's a myriad of other things. Then I show the CO2 gas region here at 4.27 microns, and then CO at 4.69. It's not really so noticeable, but you do see something of a tail. The solar direction is pointing here in the bottom right direction, is from my perspective. And the tail, you kind of see that there's somewhat of an extended profile in the opposite direction from the solar direction. So here's what the spectrum looks like. It has, well, this is the reflectance spectrum. So it is pretty flat between 0.6 and 2.6 AU, but I will note some features here. First, I want to highlight the work that is done by a team led by Penilla Alonso, who I think is University of Oviedo now. She used to be at UCF, University of Central Florida, but she's moved to Spain. So this is showing the spectra of the 3 main types of Kuiper belt objects. You have the organics-rich objects, which between 0.6 and 3 microns have kind of a break in the slope here and then kind of go blue. But then they have this huge absorption feature here around 3 microns, and then lots of organics. We call these the organics-rich. Where in the middle here, you have objects which have a 3 micron feature as well, but they have more CO2. We call these CO2 rich objects. They have a CO2 fundamental line at 2.78 microns, as well as at 4.27. And then the bottommost here is we call the icy rich objects, which have very deep H2O ice absorption features of 1.5, 2 microns, and of course 3 microns with a Fresnel peak, which is typically associated with ice, with water ice. So comparing these to UN271, we would say that the spectral type is most similar between the ice and UN271. They have water ice features at 1.5, 2, and 3 microns, and UN271 also has a Fresnel peak. So I'll also talk about the gas. There's also very obviously there's these huge gas emission features. You have CO2 gas here. We have CO gas right here, and the CO gas also has a doublet. We see the P and R branches there. So using the PSG, we determine the ratio in production between the CO and CO2 gas production is about 10. And if you calculate the active surface area, keeping in mind that this comet was observed at about 18.2 AU and CO2, it implies an active surface area of greater than 100%, suggesting that this is a hyperactive comet. And you can see that in the IFU images, in the continuum subtracted IFU images of CO2 here, right here, and on CO, you kind of see some hint of it. Basically, this is an enhanced version where I divide out the distance from the optocenter, is that the CO looks more like a blob, but there is some directionality with the CO2 that goes in the direction in the anti-solar direction that might suggest that the CO2 and its hyperactivity is caused by the sublimation of CO2 ice grains, which is evocative. Oh, thank you. Which is evocative of the Michael-Hearn hyperactivity model, where you have a more volatile species driving the activity of a less volatile species. I'm not going to go into too much detail because I have lots of other cool stuff to show you. Another thing that we see over the 4 observations taking place over a couple of years so far, we see evolution in the activity. There's evolution in the CO, but I'll highlight the CO2 here, is that on the CO2 continuum subtracted image in the IFU, we see, and initially we just see kind of a blob here, but starting around June of 2023, and July of 2024 and October of 2024, we start to see the formation of a spiral. This implies that perhaps the mechanism for producing CO2 is evolving, where we now have surface level CO2 starting to become active at mid-latitude, and as the comet rotates, this creates this kind of spiral structure. And if you use the speed of sound and CO2 gas at this distance from the sun, it implies a rotation period of about 15 hours, which I think is typical for Kuiper belt objects. But it is some indication of the object's rotation period. Now, the next thing I'm going to talk about is the CO ice depth. We can simulate the depth of CO ice as a function of the amount of time that the comet spends at the interior edge of the primordial transitunian disk, 35 million years, 70 million years, 140 million years, where black is 35 million years and blue is 140 million years. That at the least amount of time, the depth is at about 400 meters, and at 140 million years, the depth is about 1,500 meters. So we have more or less the depletion of CO ice starting from the surface and propagating inward as the thermal wave travels through the surface of the comet. It depletes the CO ice. And when the comet leaves the Oort cloud, we can also simulate the refreezing, the secondary refreezing of the CO back from CO gas into CO ice, which creates the structure here. The CO ice lines, while the comet was still inside the Oort cloud, is given by these solid lines, where the refreezing boundaries, as it's leaving the primordial transitunian disk, is in these dashed lines here. So now when the comet returns back to the planetary system after being in the Oort cloud for 4.5 billion years approximately, we can calculate the onset, what we would predict the onset of activity would have to be for the residence time that the comet spends inside the primordial Kuiper belt before being ejected into the Oort cloud. And as you can see, for 35 million years, it predicts an onset of activity at about 60 AU. For 70 million years-ish, it's more in line with what we actually see. And if it's 140 million years, we don't see the comet become active at all until it's on its way back out after passing through perihelion. So what this implies is that the comet spent about 50 million years in the primordial Kuiper belt before being ejected into the Oort cloud. And this is a variety of different models we've run here, but it seems that the average, let's see, the expected value is about 50 million years, which implies that the Oort cloud was formed no earlier than 50 million years after the formation of the solar system. So here are the contributions, and that's the end of my talk.
I'm confused about your model. If you go back on the depletion of CO as a function of depth, if I understand that curve, you would predict, the next one before that, you would predict that anything greater than 2 kilometers in your cloud shouldn't have any CO. No. Yeah, because your depletion depth.
Smaller than 2 kilometers.
Yeah, anything smaller than 2.
Said greater.
Oh, I'm sorry. Anything smaller than 2 kilometers shouldn't have any CO. Is that consistent with observations?
I think the furthest active object we've ever seen coming in from the Oort cloud is UN 271, which has 140 kilometers. These other objects, K2, there's a couple of others that were highlighted before in the review talk by Jessica. They were seen to be active much closer to the sun than this. And it is not so clear from those if it's CO that is driving or CO2. In this case, we know it's a CO that is driving the activity because we see the onset of activity starts at 26 AU, a great distance beyond which CO2 can become active. But for these other objects like K2 and this other 2010 object, and a few others, they are discovered to be active at around 20 AU, where you can have, at some weak level, sublimation of other volatiles, including CO2.
But don't we see CO emission from comets? It's disassociated from CO2.
Those are when we detect CO from comets, this is the most distant detection of CO in a comet at 18.2 AU. Other detections of comets carry CO is much closer to the sun. So at K2, I believe, was at 2 AU. There's some centaurs that were observed around 5 AU. I believe the ones from Bin Yang's program were observed inside 10 AU. This is a distance well inside which you can have CO2 be active and have enough energy from the sun to photodissociate into CO. The photodissociation length scale, let's say, is well inside the confines of the near-spec IFU in these cases. And there's also some other observations which occurred with ALMA, which were quite close to the sun as well.
That's interesting. So you're making a prediction when we do comet sample return, you shouldn't see any CO if the object is a kilometer size.
No primordial CO. If you have CO produced by secondary processes, yes, but primordial CO, no.
I just have a quick question in between. Maybe a stupid question, but isn't the accretion of CO in the primordial Kuiper belt limited by the lifetime of the protoplanetary disk?
Yeah, so this is something that I am looking for answers for is just how good, how efficient are objects in the Kuiper belt at accreting CO? And again, this is not my field of expertise. You said this was a dumb question, but no, it's not. I think you know quite a bit more about this topic than I do, so I'm really the one asking the dumb question here. And that question is that it seems that in the midplane of protoplanetary disks that you have very cold temperatures where CO can condense at the distances of the Kuiper belt. But I'm not a protoplanetary disk expert. I cannot.
But after 5 million years, you don't have the gaseous disk anymore, right? So you cannot accrete.
Yeah, but the planetesimals are built by that.
No, but this is the exposure to the solar irradiation. So the idea here is that the body accretes its CO, but then loses CO on the outskirts because the disk goes away, becomes optically transparent, and it's irradiated by the sun. And so Dina Prelink computed how deep would be CO devolatilization as a function of time due to solar irradiation once the disk has been removed. And if the disk was dusty, because it was sort of debris disk, then of course it takes even longer to get the depth of devolatilization.
Yeah. I don't understand very well the argument why the comet should have a formation age of about 50 million years.
No, it's not a formation age.
So this is the formation time of the Oort cloud, not of the comet itself. We think
ejection age.
Yes.
So
The ejection age, not the formation.
Yeah, ejection age.
Because from that point, solar irradiation is negligible. But if you need a depletion of a couple of kilometers.
But why not, instead of 50 million years, 30 million years, for instance? Why is the reason?
Because the surface devolatilization would have been too thin, and the comets would not have turned active at 26 AU, would have turned active at 40 AU or something like that.
How you calculate the radiation that the comet receives? Because the sun was fainter at that time. Did you take into account that the sun was fainter?
No, and this indeed, so these are all lower bounds. It's not taken into account that the sun was fainter, and it's not taken into account that the disk was probably dusty, because before the ejection there was collisional activity, so it was a debris disk. So these time scales that Dina computes are actually all lower bounds, because if you receive less radiation, of course you need a longer time to deplete the same thickness.
But we have an upper bound to the same depletion time based on the survivability of the binaries.
That's what Bryce said.
So it's pretty well constrained if this argument is right.
I think we can leave some of this for the discussion hour after this. Let's thank Bryce and all the other speakers.
With a panel discussion. And since I didn't have a talk, then Hans asked me if I would organize it, which I'm very happy to do. I really enjoyed this broad range of talks that we heard today and yesterday, and I certainly learned a lot, very inspirational for me. So we have a panel here consisting of Hal and Julio and Jessica. They've already given their talk, so we know who they are. And it's meant to, we will discuss until 1640 at the latest. I also need to catch a plane. I think others need to do that also. There'll be no delays. You cannot read the questions behind you, and I will just, you can read them there. I just thought a little bit today about writing some guiding questions. They are certainly not written in stone. We can discuss other things also. What I'll do is I'll just go through this question quickly. We'll go through the panel first, and then I will invite for the audience, and then we can switch forward and back. We can skip some questions, and we can always take in other questions. But what I had in mind to talk about a little bit sort of more large-scale picture is what will be in 10 years from now, a decade from now, how will we think differently about our solar system? We heard a lot today about the classical Oort plot and where we are today, but what about 10 years from now? Particularly what we will learn from, we heard a lot from LSST, we heard about Comet Interceptor. We did not talk about Lucy at all, actually.
Well, it's not really
but
relevant to
it
the
may be
Oort cloud,
relevant,
correct?
and since Hal is here, I wanted to add Lucy
Makes
also.
comets?
So
Excuse me?
discussing,
Makes comets?
discussing also what we learned by studying Jupiter Trojans. We had a lot of discussion about Planet 9 and interstellar comets, and I also wanted to sort of bring on and say, what will we learn from this? We heard a lot about how to look for Planet 9, how to look for interstellar comets, but I also want to talk about, again, maybe 10 years from now, what will we have learned from Planet 9 and from more interstellar comets? What is the new thing that we will learn from? It's really exciting, I think. We did not talk much about laboratory work. Elisheva has left, unfortunately, with the cosmochemistry in the laboratory. There are also people working on comet activity in the laboratory. We did not have much talk about that here. I don't know how relevant it is for Comet Interceptor or other things to do more laboratory work, but if anyone wants to discuss that, so that would be good. Then we talked actually about generalizing away from the solar system. What is an exo-Oort cloud like? We heard from Hans Rickman about super-Earth systems and systems with hot Jupiters, how they would be bombarded by comets, but how would the Oort cloud look like from that kind of system? Of course, that requires you to know the architecture of the giant planets, but we do know more and more from exoplanets now, and also planetesimal formation. To make our own Oort cloud, we need 10, 20 Earth masses of planetesimals to form outside of Neptune. Who knows how? Maybe how do they form around other stars? Maybe that's something to think about also. And of course, any other points that people would want to bring up. But maybe we can start with the first point. And Hal, you actually the one who sort of formulated that. What do you think we will know 10 years from now that we don't know today? If given
Well, if I had to make a prediction, I would predict that we will come back 10 years from now to a meeting like this, and we will all agree that the Oort cloud was captured from other stars.
There you are.
Okay. So, I just think it's a matter of time that you're all going to come around to the correct way of thinking. I mean, it was all material that was born in the same star cluster as ours, but the dynamic shows that if all stars produce the amount of planetesimals that ours do, even if it scales with the mass of the star, and they're ejected early enough that the Oort cloud will be dominated by things that are captured rather than things that have come through the come through the standard picture of Oort cloud formation. And it's just a matter of whether the assumptions I just said are correct or not. Right? But
so, what are the predictions for the inner Oort cloud from that model?
I'd have to go and we looked at this, but I don't remember what the answer was. Right?
That might be a distinguishing feature.
Yes,
that will sort of bring everybody around, or
yes, right. But remember, capture probabilities of even the inner Oort cloud, if it's done in a star cluster like people have been talking about, is only 10%. Right.
Sure.
Right. And
but
so
I'm thinking of the orbital, inclination with respect to the ecliptic.
Yeah.
Another comment here?
Then you are just shifting the question, because then there is the problem of forming the Oort clouds of the stars from which we would grab the hours.
No, that dynamics actually works pretty well, right? So the basic picture, and I don't mean to sideline this whole thing, right? But maybe I do. But the basic idea is that you have an embedded star cluster that fills with comets as these things are ejected from their planetary system. If you look at the size of these embedded clusters, they're about the same size as the Oort cloud because it's set by the tidal radius of the galaxy, right? Both are, right? So you fill this area filled with comets, and then when the cluster evaporates, just some comets happen to go off in the same direction as the sun, and they become captured, right? So that dynamics actually works. And as I said, what we showed is if you can eject planetesimals at the same rate that our system did from all the stars, right, that process should dominate versus the one that we currently believe.
But looking at the question, I don't think Comet Interceptor can test that. Lucy can't probably test that, at least very easily, but LSST might. How could LSST test that?
So one of the things that I think is going to be diagnostic is the activity of comets at large distances, right? And because one of the things that I think this model would predict, and I'd have to go back again and look at the numbers, and why I started thinking about it again, was that most stars are M dwarfs. So the comets would form at a much lower temperature, while the chemistry would be similar because it was all built from the same star cluster, right? This model would predict, I think, that a lot of comets are formed at a much lower temperature than things that we currently see today, which is why I kept asking, you know, this question, why do we see a lot of CO activity in our comets when they spent a lot of time at 20 AU before they got ejected? Right, and I think that that's going to end up being a critical diagnostic from an observational point of view.
Well, I've got to sort of say my previous comment. I think a big thing we're going to learn from LSST is more about the inner Oort cloud. I think the inner Oort cloud now is still somewhat of a big unknown.
Oh, yeah.
So as we get observations of comets, inner Oort cloud comets that are coming into Neptune crossing orbits and things like that, or beyond, hopefully, we're going to get inclination distributions, we're going to get better estimates of numbers, and that's going to, whatever the formation mechanism, we're going to be able to actually talk about it rather than guessing 10 years from now.
Were you going to comment on that?
Yes. Going to other point, my prediction regarding the second point is that from now to 10 years in the future, I guess that we can either have discovered Planet 9 or at least put much stronger constraints on the existence of such a planet. Probably, if we didn't find anything in the next 10 years, I would say the existence of a planet of several Earth masses will have to be discarded. Probably this
maybe to be a bit provocative, what if we don't find Planet 9? Has it been a waste of time? Has it been a waste of time then? Or?
Well, it's a good idea, but I guess we are just on the right moment with all the searches, just to either to find this planet or just to reject the idea of a big planet over there.
Do you have a view of that? Or?
I think it's a question of who's a waste of time. I think it depends on for who, right?
Yeah.
I honestly think it's that Planet 9 is just icing on the cake, right? I think it's really about finding the planetesimals because you need both to understand the story, right? And also, even if you find Planet 9, I still don't understand what things are actually being perturbed by Planet 9. Were they there the whole time, right? Was something else going on? I know the predictions, maybe that's not true, but even finding those objects would then mean we can start looking at surface properties and compare that to what we're seeing in the Kuiper and elsewhere, right? So, but I also think if it's not Planet 9, then we also are going to get a way better understanding of the structure, and then other things come back into play. So I just view Planet 9 as one of the scenarios. So I think it's still quite useful.
Of course, a scenario with a very big public attention. So if to that degree, it can be, I guess, useful also for just highlighting this possibility. I don't know how unethical that is.
It's useful for defending the cadence to get certain parts of the northern ecliptic, but I think I feel like that's the way we should be viewing it. Planet 9 is one of these theories. I still think, as an observer, I don't like how some of the statistics are being done and what objects are in there. And I think some of what I saw here, I think as observers, and I think we need to be told what objects should we be using to do these statistics, which would help us, because we're going to start finding things, and if we're doing the wrong comparisons or including the wrong objects, I think guidance there is going to be helpful.
So let me ask you a question. Of the inner Oort cloud population, and I agree with Tom, right? Understanding that population is key to understanding a lot of the early history of the solar system. How small an object can we see at 30 AU? You don't go that faint, right?
I mean, I guess the sense is that if we know 5,000 KBOs today and we're going to 38,000 is the latest prediction, that's still a lot. And so, and also then we all get colors too. And so I think the fact that we now have a huge sample with colors, now we get to play some more interesting games about, right, contamination and other things, right, that I think play into some of this. And so...
But you didn't answer my question.
But I don't think I actually have in my head the size of the object, because I live in H.
It's still going to be tens of kilometers.
It's still tens of kilometers.
That's what I thought.
I think. 100, yeah. But like, you know, but for me, I think is that still, you know, for me, it's a sheer number that starts getting us into looking at the different things. And also just that it's well calibrated. So well calibrated, it's now what we didn't find. So for, you know, I think that's interesting of like, we can put now, I think probably the best constraints on how much material is out there, regardless of Planet 9, right? Because LSSTs can be so calibrated and so big coverage. For OSLAS and CFEPs have been great at that, and so is DES, but DES is, they're all small area. And so I think getting bigger then helps, especially if they are smaller numbers of these things, it's gonna help us at least push up in terms of the constraints. So that's what I'm more excited about. In that sense, both what we can find and not find, just because LSST is so well calibrated.
Hello. Just a comment on the waste of time. The discovery of Pluto was also the result of searching for an object that was perturbing the orbit of an outer planet, and it turned out that you found Pluto. That was not what they were looking for, but you still found something cool. So.
That sort of shifts us directly over to the interstellar comets. Will we 10 years from now think, great, we learned so much from these? Or will we think, yeah, we have a couple of handfuls, some of them look like Borisov and some not? Just to be devil's advocate again, what are people's views of the next 10 years of interstellar comets?
It's going to really depend on whether we find, you know, a handful more or whether we find tens more. And, you know, how common these things are, I think, is the first interesting question.
Maybe the question could be, do we need a project entirely devoted to search for interstellar objects because of the fast movement that they have? It's very different from the other kind of objects like TNOs, just move very slowly. They actually move very fast, and then we just miss them. Either we have a project entirely devoted to the search.
My understanding is they're just as hard as NEOs. So yeah, there's an argument that other surveys have missed them. So that, right, that because you're looking at different populations, and traditionally our surveys have all been, I care about inner solar system, so I don't care about outer solar system. Outer solar system, you're moving, you know, closer in than Jupiter, I don't care. So my understanding is the LSST pipeline, because I've asked, has been already, the moving object pipeline has been tested with simulated interstellar objects. And so it effectively, right, they're faster, but they're the same challenge as NEOs. So they're confident that given all the simulated NEOs and ISOs they've put through, the Helio link or the adapted Helio link 3D has no problem with them. So I don't think that it's going to be an issue for Ruben that it's going to miss things because of the algorithm. So I'm pretty confident we'll be okay in that sense.
A comment on that?
Yeah, a couple of comments on that. Michele Bannister pointed out in her talk, as part of the University of Canterbury group, I've been involved in a number of the interstellar object simulations, and we noticed that because of the southern pointing of LSST, there are a bunch of interstellar objects that if they end up with their perihelia in the northern hemisphere, we will just not get any observations of them. So it's not that LSST will miss the things that it should be able to see, it's that it's also just not looking everywhere. And so the plot that Michele showed of sort of historic surveys trying to look for other objects, people have specifically avoided the galactic plane for obvious reasons, but obviously this is where the ISOs will be coming from as well. So the reason for the CFHT inbound ISO survey that we started was, let's look at more closely where these objects are going to be coming from to see if we can find more of them on their way in, when they will be slower fainter, but if we stare at the same spot, maybe we will find them a bit further out. So it's supposed to be complementary to LSST. LSST will find some ISOs. But again, I think Colin's point that how many of these there are is the biggest unconstrained parameter for how useful the LSST sample will be.
But I think whatever we learn on the ISO, since we only have had 2 objects so far, whatever we learn will be very interesting and new, even if we don't find any, because we have had 2 within 2 years, so it would be surprising not to find any others. And they are very different, so if there's 2 classes or if there's a wider range of diversity, everything will be just brand new.
Yeah, I guess it can tell you a lot about planetary formation in other systems, and Oumuamua clearly being a different beast, right? Isn't it?
So the question is really how common that is.
Yes, exactly.
Right? And so I was just going to say, let me just quickly make a comment, because I make this point with Lucy all the time, right? Is that, look, if I will be disappointed if we get to the end of Lucy and haven't found something we totally didn't expect. That's how science is done, right? And that's what makes science fun, right? And so all these things that we're talking about, right, I will be disappointed if the picture of the solar system that we have at the end of LSST or any of these other things is what we currently have, right?
Yeah, so it's related to this. It's like one of the things when it comes to the ISOs and to LSST, one of the things I think was going to be very interesting is whether or not we find a significant population of small things coming out of the Oort cloud that behave like Oumuamua. That we actually find when you start getting down to the 100-meter scale cometary nuclei that we just don't see many of, that you get this very low activity or no activity things. Because the environment in the Oort cloud and the environment in the galaxy is basically the same. And so we were very lucky with Oumuamua. It came very close to Earth. That's why it was detected. And with LSST, you get a wider volume that you can detect inactive things on Oort cloud-like orbits on 100-meter scale objects. And so I think that's a very interesting population that will be good to look at. Do we see a significant population of things that have been devolatilized entirely?
We also heard about returning ISO, so to say, that left our Oort cloud and came back, I guess, even shortly after. What is the probability? I didn't know, I don't remember. What is the fraction you expect of these that were actually just kind of leaving for a little while? Is that an interpretation that we could think this might be part of our outer Oort cloud we are seeing and interpreting as an interstellar comet?
I mean, yeah, I think the point is that the environment, in terms of the physical evolution of things, if they're in the Oort cloud or in interstellar space, basically the same. So in terms of what you might expect in terms of thermal evolution or everything, I think the really interesting thing is going to be the very small end of size distribution, which we just are not yet sensitive to. And that also comes back to this: do we have CO? Do we have more CO2, or do we have, what's the... I think I would add JWST to your list of interesting things the next decade. Because so far we only have a couple of comet spectra from JWST, and they're both very surprising and different. So a bunch more of those would also be helpful.
Yes, about the interstellar objects, that if we have 2 macroscopic objects that were found to move on hyperbolic orbits. But as far as I understand, a small fraction of the bolides that we observe are found to move in interstellar heliocentric orbits. And I don't know how accuracy are these orbits, might be not, and we cannot say for sure that the orbits, the heliocentric orbits, are really hyperbolic. But this is an interesting point just to observe, because of course, if 2 bodies were observed, 2 macroscopic bodies were observed, many many more smaller objects should have to be observed in the last decades.
There is certainly interstellar dust, so why shouldn't there be anything in between in terms of sizes?
But remember, the formation mechanisms are very different.
Yeah.
Right. Dust can form in the atmospheres of red giants and things like that. Right? So it doesn't necessarily mean they're related to macroscopic objects.
I think Bryce first.
So I have kind of a contrarian opinion, and doesn't have to be the popular one here. But what if Oumuamua is not as strange as it's been discussed to be? What if it's actually more like an ordinary solar system object? What does that change about our picture of interstellar objects?
So you mean that it's more like an asteroid or more like a comet?
It's more like a typical solar system object, something we've seen. Say we see a similar number of objects with, say, a goodly number of objects with similar axial ratio. It certainly has colors similar to solar system objects. The activity, low-level activity we've seen in comets that have basically no coma but exhibit significant non-gravitational accelerations. I don't really buy the argument that Oumuamua is so strange.
Well, the light curve is anomalous.
We've seen light curves like Oumuamua and asteroids in the solar system.
I don't think we have.
Oh yes, magnitude 5-to-1 axial ratio.
They're not common, but again, this is my point, that maybe it's just because it's unusually small. We don't have many good observations of things that scale. I mean, it got a lot more. It got a lot more observation time than the average 100-meter NEO does because it was interstellar. So it could just be that we haven't characterized a lot of things that small that well.
I've never viewed Oumuamua as being incredibly strange. Neither Boris have. I mean, there is at least one comet that has stranger compositions, right? But I think we all expect it to be similar, right? Yeah. Or at least hope that planet formation is similar everywhere else, right? So things are too wildly different.
Julio, if I understood you correctly, you were questioning whether the orbits of Oumuamua and of Borisov were, the error bars.
No,
because
I guess
the point that
I think that the orbits of these objects are interstellar. Maybe I am a bit surprised that one of them is very active and the other is inactive. But no, what I'm saying is about the bolides that are just chunks of material, a few meters size, that are observed in interstellar heliocentric orbits.
Those are affected by, because what is deciding is not the value of the eccentricity, because for the same velocity at infinity, the eccentricity is just a measure of how much the orbit is tilted by the central body, which means if the periastron is small, the eccentricity tends to 1 for the same velocity at infinity. I don't remember by heart the formula, but it tells that. Now, so the point is that to ensure the true nature of the orbit is the deciding thing is not the value of the eccentricity, but the value of the velocity at infinity. Yeah. Now, for the bolides, it's true that they are affected by enormous biases, so those are not credible. Whereas for micrometeoroids, there has been a long querelle among experts, but now it's recognized that there is at least one apparent stream of micrometeoroids which seems really truly interstellar in nature. At least one.
Okay, I think I want to move on this great discussion, but I also we had a lot today about cometary activity actually, and I wanted to ask, to what degree do we need more laboratory work and more modeling to understand this activity? And Jessica, if you want to take over with this one, how much do you rely on experiments? Yeah.
So the thing with cometary activity is that, we observe a macroscopic coma in the telescopes, or even with Rosetta, we get global production rates and things, but we don't have a very strong microscopic understanding of what happens in the surface that leads to the ejection of different materials at different times under different conditions. What we know from Rosetta is that it's complicated. It depends on where on the comet you are and at what time you are. So it's not as uniform as simple models could have been while we had less data. And I think laboratory work can help in the sense that it's, so if you make a computer model of cometary activity, you have lots of parameters that are essentially unknown: porosity, composition, the way the materials are mixed, and the way heat is transported. And in the laboratory, you have the chance of knowing better what you actually have. And if you would succeed to make a computer model that at least reproduces the laboratory measurements, that would be, to me, that would be a first step in a good direction.
Yeah, but I agree, and there's I think kind of the opposite of that is that with models, you get what you put in. You put in some physics and you get that physics. You only get surprises where those things cross, where effects cross. Whereas in the lab, you can actually see things that you can't model, which is kind of weird. Of course, you have to set it up. But I think the problem, Dina Frielnik and Barnum, they've tried these things. I think it's really hard to simulate a bloody comet because we don't have the right gravity, we don't have, everything is wrong. And putting it together, actually the Max Planck Institute next to the NPS, the one on dynamical systems or something, Holly Capello, she had these these tubes where air is coming from the bottom and can lift material and have it there floating. And you know, you have to create really clever experiments. Maybe actually in the next space station, after the ISS dies, you can actually make a lab to try to make comets in space, because we really need conditions that on Earth is really hard to do. But I agree.
So gravity is
Sure. But even what we see on Earth is currently not reproducible by numerical models to a large extent. I mean, Bastian Gunther has been doing that, yes, and they see that their simulations behave rather like comets. So things are being lifted and ejected, but still there are no computer models that can kind of reproduce that.
Colin, is experiments and models, is that part of the Comet Interceptor preparation at all?
I mean, we talked to the people that are doing these experiments. It's not like a directly part of the mission. We're sort of far enough away from actually having data to really doing that. But I mean, you know, we talk to Coffee Lab people and all this.
Yeah.
So.
Bryce?
I think we need more lab work on amorphous water ice. Very hard to tell from the spectrum if a comet has amorphous or crystalline water ice. The optical constants are not so good, and it makes there's lots of degeneracies. I think we need more lab work investigating the differences between spectrally between crystalline and amorphous water ice.
Yeah, that is true for many more materials. So the optical constants seem to be a huge bottleneck for these models, the lack of knowledge on the optical constants.
Yeah, it's actually linked back to planet formation. There also we also don't know the sticking properties of a lot of these materials, which is a real hole in our knowledge still when you do planetesimal formation models.
Yeah.
So I agree, we have more of that work. It's okay. Okay, maybe we can move sort of to the last one. Maybe it goes a little bit to the first one with Hal saying it doesn't matter. But my question was a little bit with the Oort cloud. Depend on the kind of, we know from exoplanets now, the results are probably not typical. Even giant planetary systems are probably really different from the solar system. Will they produce different Oort clouds? Or does it not matter in the end since they're all sharing, so to say? And you said your prediction was it would be M dwarfs creating most of the planetesimals, maybe?
Yeah. I mean, clearly the planetary system matters on whether you form an Oort cloud or not, right? Unlike some of the comments that were made earlier, I tend to think you'll get much more ejection than and more anemic Oort clouds, right, than maybe the solar system would produce.
But don't you need giant planets to make the Oort cloud? If M
no, Jupiter and Saturn would eject everything, right? So you need Uranus and Neptune.
So you need some more, but still around M dwarfs, we don't even know if you get 10 of them.
But the critical parameter is the ratio of the escape velocity from the planet to the circular velocity around the sun.
Right.
right? And that's the critical question. So if you're around M dwarfs, right, the orbital velocities are also lower. So a planet like Neptune is more likely to eject things.
Yeah. So maybe a Jupiter became a Neptune around an M dwarf because it didn't grow big enough to accrete gas, and it would still be a good Oort cloud creator, so to say. Yeah?
No, it wouldn't, because it would eject things rather than putting it in the Oort cloud, right? The thing about our Oort cloud is there's a very narrow energy location where you have to place things in order to get it trapped. That's why it's so inefficient, right? And I could easily see that a lot of planetary systems wouldn't ever put anything in there. It requires particular ratios of these parameters. So, I think that work needs to be done. I'm not arguing to anybody that they should go off and make up planetary systems and just see what they do, because it's all going to be dependent on what we see. But as we start getting a better understanding of what outer planetary systems look like, we should be able to answer that more.
I was thinking of another mechanism to sort of fail at making an Oort cloud. I think Morby mentioned that, say, around M dwarfs, the Safronov number gets large, at which point you accrete more, the forming planets accrete more objects, and you lose a lot of bodies.
I don't think that's right. I mean, the Safronov number is this ratio of escape velocity to orbital velocity.
No, sorry, I'm not thinking of Safronov. The geometric size, what do you call it? The geometric size of the bodies compared to the hill radius.
Okay.
What's that number?
It's the equivalent.
That's the equivalent.
It is equivalent, but so if like in STIP systems, right? At short orbital periods, the physical body, assuming everything is, roughly terrestrial density, fill a larger fraction of their hill radius geometrically, which means they sweep up bodies instead of ejecting them.
Remember, it's the mass ratio and the semi-major axis.
Well, and the combination is the period.
Right.
Yeah, so the period is the critical number.
You just said you wouldn't encourage anyone to do this. It sounds like someone should do this, because there seems to be actually a lot of uncertainty.
I mean, there's analytic scaling, right, that Scott Tremaine did years and years and years ago, that you could turn to in order to get a zeroth order understanding of this problem. So we have that. The problem is we do not know what a typical planetary system looks like.
Yes.
Right? And, what Morby was talking about is you see all these close-in planets around M stars. Yeah, I agree with him. Those would not form Oort clouds, right? But you don't know what's happening at an AU, right? No. And that's where the Oort clouds would come from in these systems. And we don't have any constraints.
You also don't know where the planetesimals form.
That's right.
That depends on the stellar mass, right? So.
My opinion is that Oort clouds is not a problem for the next 10 years, but it's a problem for the next century.
Yes.
I am afraid that we have to wait to the next generations to have an answer.
But if we start to discover, if we go to smaller nuclei coming from the Oort cloud, and we start to discover objects that have chemical compositions that, like you were saying, you can't explain them. Like they have CO, and they shouldn't at that size anymore have CO if they formed the way we think they formed at the distance we think they form, means they must come from other systems, not from ours. If we find objects that just chemically, they cannot have formed in our, in terms of volatile ratios.
Yeah, as I said, I think this idea that we capture the Oort cloud is a testable idea.
Yeah.
Right? But this is an issue of what extra solar Oort clouds look like around other stars. And I don't see how I agree with Julio. We're not going to get constraints on that. I don't even see how to measure it, right?
It's possible in 400 nanometer, 400 micron observations, like CMAPs.
What is that, right? So what is 400 micron observation?
So like Planck cosmic microwave background.
So you would see like a glow around all the stars, or
I don't know what it would look like.
The optical depth is really low.
Yeah, very low.
Really low.
So this is a question is exactly how do we define inner Oort cloud and outer Oort cloud? It seems that there's multiple ways of defining these terms. Is there a strict definition? Because you have like these sedenoid-like objects where you say, okay, they're like inner Oort cloud, but their ejection mechanism and population is very different from what we would say is the true inner Oort cloud. And then there's kind of this not really well-defined boundary between, okay, 10,000 AU, okay, inside 1,000 to 10,000 is inner, and beyond that is outer. But it seems like that can shift quite a bit because for the objects which are definitively dynamically new in outer Oort cloud, the actual boundaries could be as far as 40,000 AU. So is there a consistent consensus on the definition of these different zones?
I would say it doesn't matter.
Yeah.
Right? It's like asking what a planet is. Believe me, I'm
Get very
involved in
excited
this
about it.
argument much more than I would expect to, given where I'm at.
I agree.
Right? I think the answer is going to be what the semi-major axis distribution of the Oort cloud is, and what the inclinations and eccentricities are as a function of semi-major axis is going to point us towards a model that has all these dynamics in it and all these pathways to get there. And we're going to be able to, hopefully, once we have a good picture, which hopefully LSST will help us, point us to a direction of which of those mechanisms are most important.
I think
Yeah, just a comment. I guess using this chemical argument that we'll be able to sort out these incomers by studying their chemical composition. I'm a bit worried about the fact that we don't understand a number of quite substantial fractionation processes in our own system. So that might be quite tricky to do.
Yeah, true. I was just going to say that I think the definition of inner Oort cloud is a moving goalpost of the part of the Oort cloud we still don't see. That's what it is. And the more we probe into it, it becomes simply the Oort cloud. It's just growing the visible Oort cloud, the one we're sampling. It's basically an unsampled space. We know things must be there, but we just haven't sampled it. I think that's because the definition doesn't matter.
Well, but I do, as I said, I think physical processes do. Right? The sediment population, I don't think you could form it very easily without having us start the Oort cloud formation process inside of the star cluster.
Yeah.
Right? And so that's why I'm saying it depends. All the characteristics of the Oort cloud as a whole is going to give us an understanding of when things formed and, at least relatively, whether, the sun was in the star cluster, when it left the star cluster compared to when the gas went away and the protoplanetary disk. Those are the kind of things that are going to be able to help us figure out what happened. Whether you call it doesn't matter, right? Whether the sun formed closer to the sun and migrated outward, right? Those are the kind of things, if we had a really good consensus of what this structure looked like, we should be able to answer.
Yeah, that's true.
We're approaching the end of the panel discussion. I had one. Any other points?
Yes.
Is there anything anyone wants to bring up here? I see the raised hand here. Julio, please. Yeah.
Yes. There is a problem that I noticed many people say such a comet is a new comet. But I found that we don't know exactly whether it's a new comet in the sense that it's coming for the first time from the Oort cloud. And the reason is that now comets, the original orbits or comets are not being computed nowadays. They used to be computed in the past because there were catalogs bringing the original energies of the comets. That was mainly done by Brian Marsden and it started with Edgar Everhart. But then when that was continued by Gareth Williams, but when Gareth Williams left the Minor Planet Center, nobody cared about computing original orbits. And then there are some scattered work made by some Polish people, mainly Krolikowska, that has done some computations of original orbits of sun interesting comets, but that's all. And I think that we need, for comets that are going to be discovered, to have very good orbit of good quality, and to have the original orbits to know for sure which comets are coming from the Oort cloud.
Yeah, I agree.
Well, there is an easy way to get the original orbit by using horizons, the system of the JPL, because then you can ask for a specific comet to have it backwards integrated for, I think, up to 400 years. But asking for barycentric coordinates.
I did. Is that okay to do? Because I was doing that, but I thought I was cheating.
I think it's okay. What they could add to it, perhaps one could ask John Giorgini, who is the maintainer, to add the covariance backwards, so that you get an idea of the errors on the original orbit.
I did that to try to see how well do we know Q and A over time as the comet is going away, into the past. And I found, I don't know anything about that. The Q is known quite early. You determine the Q quite early, but the A is still uncertain. And I did that using that same trick, and I thought I was cheating, but apparently it's
correct.
We have a comment here in the back.
But just that for the determination of the original orbit, the non-gravitational forces are very important, and I think that the advantage of the Krolikowska work is that she's modeling these non-gravitational forces very carefully, and if you consider the proportion of hyperbolic original orbit you will find, Krolikowska is cataloged with the lowest number of original hyperbolic orbit. So I think this makes our catalog more trustable, but in my opinion. With Horizon, it was much more...
Takes into account the non-gravitational force.
Yes, but not with the same... I don't know, when we did it also with Horizon on the proportion of...
For large perihelion distance comets, it will not.
It doesn't matter. That's what I was thinking. What does the non-gravitational effect at 40 AU?
Yes.
Small,
but non-zero.
Well, no, because yes. Well, if you want to focus on the comets at lower perihelion distance, in order to have to hope to have a complete sample of comets, then you will have non-gravitational effect.
Yeah, and all the observations are in the region where you do have the non-gravitational effects already.
Yeah.
So I guess there is an empirical way to know about the effect of non-gravitational forces, because if you just take the distribution of original energies of comets, comets that have very small perihelion distances, the spike, the Oort cloud spike, tend to be fuzzy, because there are big errors due to the non-gravitational forces. And we go beyond 3, 4 AU, then you have a very narrow spike telling you that the non-gravitational forces have a very little effect on the orbits. And then you more or less can trust on the purely the dynamical solution.
It's a great discussion. I think we have to wrap it up here. So it's time to end the meeting with Bengt Gustafsson's final words. Let's thank the panel members and the rest of us for making such a good discussion. Okay. I need to run. Good seeing you. It's always a pleasure. Let's stay in touch. Yeah. Good. Thank you.
Okay, I'm sorry for breaking this discussion. I'd like to continue that instead of standing here, but I'll do my best. I want to say a few words about Ernst Öpik, who was mentioned a couple of times by Julio, I think, but that was it. He was quite a figure, and as you may know, he started in Estonia, went to Moscow, and then later to Northern Ireland, where I took up a position. He was also guest professor in Maryland, and I met him there. I spent some time there, and he was then lecturing to us about turbulence. And to do that, he brought up his wooden elm box, and in that was a hand anemometer to measure wind strengths, and which he carried along like this in the landscape to measure turbulence, that different wind velocities at different places. He already in 1950 discovered the triple alpha process, the helium burning to carbon, and discussed that in a paper which was unfortunately not spread very much. He did this independently and simultaneously with Erwin Salpeter, who got famous for it, his work. Anyhow, his major field was small bodies in the solar system. And so he wrote this paper in 1932 with the obscure title, Note on Stellar Perturbations on Nearly Parabolic Orbits. And these parabolic orbits included orbits of comets and also meteors and also possibly planets, according to his presentation. And he called all these objects meteors. And I think this fact, plus the fact that he published it in a rather different journal, which most people didn't read, made him not being read in 32. If you read that paper, he is really sketching an Oort cloud. And basic features are there. And then independently, Oort, much later, wrote his famous paper, which gave name to the phenomenon. Öpik's paper had 36 citations yesterday, and the first ones were by Fred Whipple in 1972. I don't think Oort knew about this, but still it is illustrating the need to publish in the right place.
Make enough noise.
Yeah. Öpik was, I think, humble also, very pleasant to talk to, but rather odd. So maybe that's the reason too why he didn't get the honor for this. My suggestion is let's change the word to the Öpik Oort Cometary Cloud, or at least the Oort Öpik Cometary Cloud. He deserves that.
The first paper.
I would like to just say, being a stellar physicist, that I really enjoyed this meeting. What a field you have. It's quite nice. Precise analytical theory with profound and interesting tradition, complex dynamical systems, limited chaos, that is not chaos all over, but in certain places, so certainly quite interesting situations. You have, of course, we see like advanced numerical simulations, and you have planned major surveys and planned space probes, and not the least, interesting and well-posed problems. It's nice. There are many fields in science which don't have all these things, or hardly any of them. You have that. we have this discussing the problems all the time here. I just listed these, the origin, the primordial internal processes in solar system. I would like to know more about that because I'm interested in stars and early phases in solar evolution. Key question is the decoding, that is, from your data and work on your cloud, what can we really deduce concerning the early evolution of the solar system from that? If we captured all these comets from other stars, it would be very hard to say anything special about the early solar evolution from our cloud. Of course, the role of the birth cluster, the galactic tides, stellar encounters, giant molecular clouds, planetary arrangements, Planet 9, all these things are probably or possibly affecting the Oort cloud in the present shape. It would be very interesting to be able to, and I know you do that, to try to decode this. Then the question comes in, how many do we have? And I would be keen on knowing what you think. I mean, are there more than 50% of the stars? Do they have their exo or clouds? Hands up. How many think so? One person? Majority. It would be fun to come back here 10 years or 20 years from now and hear what the answers are. Well, you don't think you do that.
I think we should have done a hands-on.
Anyhow, I guess, I mean, the study of these interstellar comets will give some more knowledge.
Photographic.
And then comes, of course, this rather speculative question. Are they important? Not only important scientifically, but also important for understanding more things, deeper things, including our own existence in any way. If we happen to have one of the few Oort clouds, then of course you could start to speculate further in that direction. I don't know. So these were just some questions, and you brought up many more. Let's come back and rejoin here 50 years from now or so and get some of the answers or more questions. I would like to hand over the word now to this fellow and also thank him because he is the man who actually initiated this and who has been driving it and contributed more than most of us to it. So,
okay, thank you, Bengt. I think I have 2 pictures more to show. Yeah. So I think we had a great meeting. In fact, from my point of view, this was fine. And there are 2 people I think we have to thank because they made this possible. And I'm thinking perhaps in particular about Veronica, who has been working like a slave since a long time to realize this. And also Pierre, of course, was around the technical apparatus. So let's thank them all. Then, this is ourselves, as of yesterday. So we're going to send out this picture to all of you.
Yeah, very cool.
And I really want to thank you for coming and making this possible. This this has been a great experience to me, just talking to you and listening to your talks and looking at your posters. So I'm really grateful to you for having come here, and I hope to see you again. Maybe at some big meeting somewhere like the ACM in Poznan next year. Or why not at some follow-up or cloud meeting somewhere else in the world? I'd be very interested in going there. So thank you all.